universe is calling you. The universe is calling me. It speaks both day and night. It's full of dark and light, and I've heard others call from light years away, and they're real and they're here. Space and time are instantly clear. Planets spin, grids in place. We can travel through space, fields and forms, math and voids. It all sings with one voice. It's home. Boundaries set, foundations laid. Sound was heard, matter made. Solar systems from afar. Names and numbers for the stars, and I've heard others call from light years away, and they're real and they're here. Space and time are instantly clear. Planets spin, grids in place. We can travel through space. It's the Lord's.
Hey everybody, welcome to SkyTour live stream. It is I don't know, what am I, a master of ceremonies maybe or something like that. Here to bring you another night of objects in the Arizona desert. I hope you guys enjoy it. I think I will. And we are going to be joined tonight by somebody else. Daryl's taking the night off, and we have a friend of ours. You can see him right there. That guy right there. See him right there? That's it. I'm pointing right at you, okay? This is Michael. He is known as Calabos in the chat. Hi there, Calabos. How are you?
Good evening, everyone. I'm doing absolutely fantastic.
That's fantastic. Yeah, and so Mike's joining us because we have a whole bunch of planned things to talk about tonight. And in the meantime, we'll also be doing some cool photography tonight, you know? So I hope you guys will stick around and enjoy it. So I'm going to get a couple other things set up here, and then we're going to Then we're going to actually start looking at specific objects. I just have one more thing to bring up over here in our observatory session, which you'll see it in a second. And we're good. So you can see the telescope is up and running. And I should put me here, and let me dump you over here. So I'll put you underneath. So here you are. So now I have you set up. All right. All right, there we are. So this is our planetarium, and this is connected to our telescope. And I'm going to do that right now, just so you can see. Okay, here we go. And disconnect and reconnect, and you'll see the little crosshair come flying in. There we go. That's where our telescope is pointing right now. It's pointing toward the west, and you can see when you look at the telescope right there that it is. It's pointing a little to the west, which is that way, right? So, Mike, tell me something. How is it going at your job?
Oh, I just returned yesterday, and yesterday was my first day back, and I was absolutely thrilled. A lot of my coworkers were overjoyed to see me because, unfortunately, a few of them witnessed what happened to me on that fateful day on June 19th. For those of you that don't know, I was at work at SpaceX, and I was on break at 7 a.m., which is our first break. And as I was sitting outside, just enjoying the morning sun, I felt my side, unfortunately, go limp. And this was a precursor to a mini stroke, or I wasn't having like a massive stroke, but I definitely felt my side go limp. I immediately called, with my good hand, I called my doctor, and she was screaming at me to
get to the ER.
Go to my boss, and go to the ER,
Yep.
have them call 911. So as I'm walking back in to the building, I'm like limping, and I was late going. I'm normally never late from my breaks, and they were actually looking for me. It was 7:20 as I'm limping back in, and a lot of people, oh, there's Michael. Oh my God, what's wrong with Michael? And I was subsequently whisked off to in an ambulance to Sentinel Hospital, and thankfully I was given a clot buster, which. From what many doctors, including my vascular surgeon, said that it saved me from like long-term effects.
Yeah.
What a clot buster does is that it's supposed to liquidate that clot that made its way to your brain.
Yeah.
Preventing any more damage that is being done.
Yeah.
And it helped. It helped, and subsequently the next day, after that medication went through me, they pretty much removed the rest of my clot in my carotid artery. It's called a carotid endorectomy, and they removed the rest of the gunk. Unfortunately, I couldn't speak for like 3 months, and I had to go do some physical therapy along with Tiffany, my partner. She helped me pretty much get back to normal as much as I could be. So once I did return back to work, it was like almost a family affair. A very, very warm welcome from my bosses, a lot of the people that were there that witnessed what happened. And I had a pretty easy day, although I did kind of push myself. I was in calibration for a little bit. Calibration is where we test the dishes, the Starlink dishes, the PCBA boards, which is all the electronics on that board. We test them in a vacuum chamber to make sure that the signal is working on that antenna.
Gotcha.
And then go from there, which is very grueling because we have 16 different stations, and each test is set up to take no longer than 6 minutes. So you're kind of running back and forth, making sure that they pass. If they fail, we have to log in the failure, and then we retest that dish. And if it fails again, then we scrap it, send it back to rework so they can work on that.
Well, thanks to guys like you. Okay, we have observatories like this because our observatory runs entirely on Starlink. It's entirely green. We're off the grid entirely with this building. We use solar during the day to build up battery power. Thank you to the landowner who has allowed us to squat SkyTour live stream on his land. And so Starlink has been a godsend. We actually had HughesNet and Viasat before this out there, which he did. But they were very slow. Now HughesNet is claiming it's going to have Starlink speeds. And I'm wondering if it's because they're using Starlink satellites or if because they're putting up one of their own sets of constellations of satellites. Do you know the answer to that?
I'm not. I don't know if I'm able to answer that.
Fair enough. Don't get yourself in trouble.
There's some stuff I can't. I apologize to the people watching. There are some stuff that I can answer. There's a lot of stuff that I'm not able to. That could violate my NDA. So I will attempt to answer as many questions as I am able to.
Okay. That's fair enough. I'm doing an autofocus routine for those that are wondering what I'm doing.
Yes, I actually. Thanks,
Tiffany. Have Tiffany come over and say hello to everybody because she's.
I'll say hello, Tiff. She's good. We recently got a grocery order, and I should be helping her, but I wanted to excuse myself first.
There she is. See right there. There she is. That's Tiffany. That's the person that tolerates him.
Yeah.
But so I just wanted people to see the face. Okay, Tiffany and Mike are actually two incredibly energetic and wonderful volunteers for SkyTour Livestream, and I can't say enough of how much they've been a great help to us in the short time they've been official volunteers. So, the equipment giveaways, all this guy and Tiffany right there, okay? That's all him, right? And he is passionate about astronomy. He's passionate about getting people out there looking at the night sky, just as I am. And so I think what we want to do is make sure that we end up with the best possible equipment for people. And thanks to Mike, he's been doing this with Tiffany for, when's the first giveaway you ever gave away? And you were doing this before SkyTour.
Yeah. Oh, yeah. It was, I believe it was the summer, fall of 2019.
Okay.
I was traveling cross country to do some construction work on a house in New Hampshire.
Okay.
And I opted to take the Greyhound bus because I've never been cross country before.
That's a cool idea.
Right? It was beautiful. It was a lot of fun. So, what we had in mind was, for those of you who may know, Cheryl Costa of ufology fame. She's written many books.
I know Cheryl. We're very good friends.
Yeah. Well, she's amazing. Yeah. I had asked her if I could use her name in a contest that we were running to give away a telescope, our first. And the contest was the Greyhound bus would stop in random cities throughout from the West Coast to the East Coast. So I would mention, if I mentioned her name in that certain city, and the person that got all those cities correct would name those cities once I got to New Hampshire, and that's the person who won the telescope. Excuse me. I don't. Goodness. My apologies.
That's okay.
All right, there you go. My apologies for that. We had YouTube running in the background, which is like a fireplace, and it ended up going to an ad. My apologies.
That's okay. All right, so that's cool. So you were giving away equipment long before SkyTour.
Oh,
but now you've chosen SkyTour Livestream as your giveaway home base, basically. I think that's really incredible.
Well, I mean, we were trying to find an outlet for this because we found that, well, personally, I just didn't want to do it alone, to be honest. And we wanted to find an outlet for our giveaways. Yeah. And we were already looking towards like creating a nonprofit, but we didn't really want to. I mean, we were lazy about it because, our respective jobs kept us from doing anything that extracurricular, for lack of a better term. And we were introduced. Oh, well, I remember you from certain groups on Facebook, and then leading up to about a year and a half ago, where I came upon I believe I was mentioned about SkyTour live stream. So I watched it and I was like, hey, I showed Tiffany. I'm like, wow, this guy is teaching like college level astronomy to people and for free. Like this maybe. And then when you mentioned nonprofit, I was sold. So that's when Tiff and I discussed about it. We did have that discussion, and we reached out to you.
Wow, that's incredible. And I'll tell you this, I'm very I haven't looked back, since starting SkyTour Livestream with Marianne Robb and Tara Diulis. I have not looked back. We have our Sunday night astronomy show, radio show on KGRA, and Tara's on that show with me along with Daryl, and Daryl's going to be taking an extended vacation, so he won't be on for the next several times, which is fine. Which we got more than enough stuff, and I've been doing that since like 2015. And
Wow.
I started with Amanda Curran as my host, and then Amanda said, "Oh, you should get Daryl." So we asked Daryl to come in. He didn't want to at first, and he did, and then he made it wonderful. We actually did a great job with the astronomy radio show, and then it became multimedia where I could then show things. We were offered, but I declined to have a slot on Sunday nights that would start at 10 p.m. Eastern time, and it would be one of these. It'd be a SkyTour live stream. So it would be a stream every single Sunday night to do this, but I opted not to because I didn't want to be locked into having to do a stream setup every single Sunday night, because people are getting ready for work Monday morning. So tonight we'll see people in here, maybe a lot of folks that might not otherwise get to hang out,
That's true.
Yeah.
Very true.
So I'm going to come over here and take us to another object here. By the way, just so everybody knows, there's some wind out there today. And so we may take longer to acquire some imagery than normal, but we'll find out. So let me come into our thing here. So here's the crosshair for those who are just joining us. This crosshair here is where our telescope is. You see it says STLS on it. All right. And if we want to go look at some really cool things, we're going to go now. We're going to check out this cluster right here. This is known as the Little Beehive cluster. All right, so we're going to check it out, and then and we're going to wait for some Starlink satellites, and then we can say to the telescope to go. And I just told the telescope to go check it out. So momentarily we'll see the telescope move. There it goes. It's moving now. And if you see me looking over here, it's because I have a gigantic curved screen. So I have the observatory broadcast coming from this side, okay, and I have the broadcast software on this side, okay, and that's the star Sirius right there, and it's heading out of the view for a moment, and I'm going to wait for us to get to a point where I can interrupt this process, because there's one other thing that I needed to address, which I didn't. I'll do it right now. So I will get to saying hello to everybody in just a minute. I'm sorry that we just got started. I'm glad that Mike is with us tonight. It's his first time on the air with us, and I'm really happy about that. Guess what that is, Mike? Oh, Mike's not watching right now. Okay. He saw it.
Did.
You saw it.
My apologies. I did. I'm trying to help out. No, I did. I saw Starlink go by. Sorry.
That's fine.
Helping Tiffany out with the groceries.
Of course. That's because you should.
You're right. I got to do my chores.
Of course. Of course. That's fair.
You're right back.
All right. Okay, so we're going to go check out this cluster, which is really outstanding. Now that he's gone, I can say that the Starlink satellites are slow today. So I'm waiting for them to bring this up here. Okay, that's where we're going. And that's what we're doing. Okay. So now the telescope has the data, and it should now move us to this location. Waiting for it. Okay, we'll try it again. Here we go. And there is the cluster that we seek right there. This is called the Little Beehive. It's in Canis Major, the great dog, the great dog of Orion, right? One of Orion's hunting dogs. And it's actually a beautiful, beautiful view in the telescope. And we're going to move it a little bit to the east. So I'm going to set up our rate of movement here to be 16 times that of the guiding motion. So that'll mean that as we move it, you'll see it move slower to the right than it might normally. Otherwise, it might go racing to the right. All right. So I'm going to say hi to everybody while we're waiting for this to show up. This is great. It's good to see everybody that's here. I see Papa Tom's here. That Calabos guy, who's he? Oh, okay. That's Mike. That's him doing his chores. Oh, he's back. Shh, don't tell him I said that. All right. Sam S is with us. Old School is with us. Hey, man. Rockstar is with us. Dagger Spells, good to see you again. And we have Papa Tom, I said hello to. Donald Kunzer, nice to see you. Daisy and Zoe Amethyst, how are you guys? Nice to see you. Right. Christine Anderson is with us tonight. Hello, Christine. How are you? And she's asking, Mark, is Sirius the dog star to the left of Orion? And the answer is yes, it is. It is to the left of Orion. In fact, Christine, let me show you where it is. If we bring up our planetarium view here, okay, you'll see right there, here is Orion, and there is Sirius right there. Okay, it's to the left of Orion, right? Actually, if you follow the belt of Orion, it starts to sort of point you into the region. It really points over here, but it points more to Sirius too, so you can see it. So very good. That was a very good question. Thank you. Michael Galea is with us. How are you? And Tim F. Woohoo! That's Tim F. And Izabela is with us. Hey, Izabela. Nice to see you as well. Michael, you're muted in case you were trying to talk. Oh, there you go. Okay.
Yeah, muted because
yeah, I see.
yeah, some stuff.
Papa Tom says I can't see the wind. Well, it's always true. You can't see the wind, Papa. I know you. I know what you mean. But you can't see the wind. But if we sit here long enough, you'll see it bounce around a little bit. But hopefully we can get around that. So far, we've been able to. We've been just waiting. Now, you'll also notice that here in our it's searching. It says it's searching here. It's searching for a guide star. Certainly no shortage of them here. And as you can see, it's already guiding up there. Okay. So for those that are just joining us, I'm just going to run through just a quick little overview. Okay, this is our telescope control box up here. This is the telescope computer. That's the telescope in there. This is me. Hi. Okay, this here is Mike. All right. He may be joining us over and over again. We'll see. This is our main view. This is our camera control cluster over here. We also have thermal controls because if you look down here, right there, it tells you that the camera is at minus 21.5 Celsius. We are cooling the camera. There's the wind, Papa Tom. See that? All right. So we are cooling the camera, and we're doing it in order to make the noise on the sensor be lessened. Now, I know that, see, there's the wind. Cosmic ray. Yeah, I realize, see, but with the wind out there, we have to kind of let it calm down a little bit. I also want to say hi to Chris from Mindforked, by the way, because I didn't earlier. Yeah. Yeah, you've been talking to the correct star, Christine. I'm not sure what that means, but okay. Yeah. It's a really a beautiful nighttime sky looking out in the looking out here in the winter sky. So not bad at all. So it's kind of interesting, Mike, when you look at a cluster like this. It's kind of interesting to think that cluster was born in a dark nebula when it was born originally, and then the stars with their hot young radiation was able to push the gas and dust away, and then they would just move as a unit for quite a while, and that's what we're seeing. Or as they move around the galaxy, they kind of move as a unit for a while. Then their gravitational interactions will make them all dissipate. We were born in a cluster like this as well. And so we have siblings. All the stars in here are almost the same, almost identical chemical compositions. That's what's cool. So
that's very absolutely lovely.
Yeah, and it's because
it's extraordinary to even think about, because I mean, it just thinking about what planets are being formed in that cluster, how many stars that we can't see beyond that, it's just extraordinary.
Yeah, and like if we'll try to take a 12-second shot. You'll notice I put 12,000 in. That's because it's milliseconds. So there's 1,000 milliseconds in 1 second. So 12,000 is 12 seconds. In fact, when I move, you'll see it probably change to 12 seconds. Yes, it did. All right. Mm-hmm. So now what I'll do is I'm going to take off that right there, and I'm going to go into our live stack. This is another window we have. And what happens here is this, we take an image, then we take a second image, we align it with the first, and we stack it on top. And we do the same over and over and over. Now we have wind, so I have it set so that we won't take every single image. It has to be a perfectly round star. With the wind, see what happens? We lose 2 so far, but if I bring it up just a little higher, I might have it in the position that's high enough just barely to start getting some greens, unless we get a burst of wind. Okay, we got a green. So there we go. So now we have a beautiful image starting. Yeah.
Right.
Yeah, isn't that pretty, Tiff? And then I can adjust the properties here and color correct this view. Isabella's with us, yep. Okay. And now I can pull this in. What happens is with these curves, what's happening is these curves are very important because this is how we manipulate the data. You see, we have the red, green, and blue curves, okay, on the sensor. And so when I come down here and color correct, what's happening is it's aligning them all underneath each other, okay? And it changes the background usually to like a black of space, okay? But then this yellow bar here is the black level. If I pull it out here, then we get noise, and we also get an extremely bright, as if light polluted view. This is extraneous data that is not that we don't want in our image. So what we do is we slide it over, okay, and again we're waiting for Starlink, Mike.
Yeah.
Yeah.
Don't worry, we're getting them up there.
I know.
We're just to let the audience know, we're actually pushing for at least 200 satellites being launched a month.
I saw that.
That's equivalent to about 8 to 10 launches a month. Yeah. So watch the skies. If you're around Florida, Texas, or in California, you might be able to see one of our rockets go up.
California.
Yeah. California.
I like this. It's okay. I like it. It's good. Everybody down.
Oh my gosh.
Yeah. So
Oh, it says hello.
Hello.
Oh, Mark, were you able to see Christine's question earlier in regards to I kind of Dog
Sirius?
Stars left of the Big
Yeah.
Dipper?
No,
Okay,
left
good.
of Orion.
Oh, left over Orion.
Yeah,
Okay.
I
Yeah,
answered that
that's
for you. I
was my
think
question.
you might have been putting away groceries, Mr. Domesticus.
Yes. Yeah. Yeah.
And by the way, folks.
And I apologize for that too. It's just we
Bad
did.
timing.
Yeah, it was super bad.
Oh, that's
timing.
fine. That's fine. There's a lot of extraneous noise sometimes, and since it's your first time, you don't know, and so I don't have any problem, letting you know what has to happen, and you guys are very, very good about this. Incidentally, Mike, tell them what you're going to do at Contact in the Desert with us. I think that's pretty cool.
Oh, all right. So this coming end of May, we are going to be at Contact in the Desert with Mark D'Antonio. It starts, or we will get there on the 28th to help set up the actual event. Because it's the 28th on a Wednesday, right? Because the 31st is when it actually...
29.
29th, thank you.
Get it right,
On
man.
the 29th, we'll be there.
Giving out
And
false information.
my apologies.
Fake news.
Tiffany and I will be there to actually help set up the event. It's held at the Renaissance Esmeralda Renaissance Esmeralda Resort and Spa in lovely Indian Wells, California. So we have been. This is our 6th year going, and this is our 2nd year volunteering for the actual event itself. Last year we ran into Mark D'Antonio and pitched a couple of ideas to him. So this is where we are today. We help out with the event for that Wednesday and Thursday, and then for Mark
And
D'Antonio's
Mark has us the rest of the days.
the rest of the days. And what we're going to be doing is helping Mark out with his workshop and his intensive. What we're going to be working the door. So the people that purchase tickets to see Mark D'Antonio will receive a raffle ticket, possibly winning them a pair of Celestron's Comatron
7 by 50s.
or the Celestron Star Center Explorer 114mm AZ mount.
Telescope.
Telescope. Whoops.
Yeah. Yeah, that's a big one to leave out. No, it's okay.
You guys are supposed to know what I'm talking about, people.
No, but that's the thing. See, most of the people here, some are really good at understanding astronomy. Others are not. Others want to be part of it because, I mean, look at the screen. There you go. That's why they want to see these beautiful images. I love it. I think it's really great. But we don't. As an astronomer, that's what I went to school for. For those that don't know, I'm a professional astronomer. This is what we look like. We have red light on all the time. No. But we're setting up observatories around the country. One of them is this one right here in Arizona. It's out in the middle of the desert. Once you drive the highway for several hours, then you come to dirt roads, which you drive for another hour, okay, and you end up out at the site in the middle of the desert where the telescope's located. It's fully green. We use Starlink for satellite. And again, thanks to the landowner who allowed us to put the observatory in. And that's SkyTour West. That's SkyTour West 1. SkyTour West 2 is going in, and that's a telescope that's going to be elsewhere in Arizona, and it's going to be 1 inch larger in diameter. This is 10 inches in diameter. We're going to bring an 11 inch out there, and we're going to be using it to do close-up views of things. So we'll be able to do deep imaging of the moon and the planets and extra sharp imagery. It's going to be absolutely stunning. And then we'll also be able to take deep views of the insides of this cluster, zooming right in. Now we can zoom in now. Yeah, sure we can. I mean, it's okay. We can do all that with this, but we're limited. We're limited because of the fact that we have a wide angle. Also, I know you want to, Mike, just make sure you don't like those packages and all those little things. That sound is piercing. You don't realize that.
This.
Oh,
Yeah,
okay.
no, it's fine. I'm just letting you know. You're good. Again, you don't know because
Okay.
the microphone is so sensitive. Okay.
Oh, our microphone is super sensitive.
Oh yeah,
boy.
absolutely. Yeah.
Even we need a better mic then, like a boom mic that doesn't pick up all the other extra sounds.
Well, yeah, I mean,
Well,
if you have a Blue Yeti, that's even better. Then you'll be on the air with us all the time. That's fine. No. Okay, so as I said, we can zoom in and so forth to these things now, okay? But, we're actually, this particular image, this particular camera is actually 100% perfectly tuned to our optical system. So we have the best possible combination that we can use. So I think that's really important to consider. And so what I want to get at here is that the next telescope is going to use another camera that is also going to be specifically perfectly tuned to that telescope's performance specifications. So you'll get to see close-up stuff without any problem at all, And then, not to end there, here on the East Coast where I live, we are setting up a solar observatory. So we're going to be able to observe the sun during the day and the stars at night. So we're going to have a system out here that's going to allow us to look at the sunspots on the sun, the explosive eruptions, the flares, and we'll be able to see all these things in intricate detail with the system we're going to put in out here. And that's going to go into an enclosure that will just lift off and allow the telescope to see the sky and close. So that's 3 locations. Right now we got 1 active. We used to have 2 active. We had the one here on the East Coast, but that was a big telescope, which is behind me now. And this telescope that is behind me, I'm not sure what we're going to do with it. I don't know if we're going to keep it. We may sell it. So that could be something that becomes a grand prize in one of our contests, perhaps down the line. I'm not sure, but we'll see. We'll see. So as you can see, if you look right here, you can see that we have 21 exposures taken and 21 rejected. That's an even number of rejected samples. Okay, and the reason they're rejected is because of the wind that we're facing out there. So just as many were rejected as taken. Okay, and so this is good for us because now when we actually have this little process in place, it prevents us from ever taking a bad photo because it's windy out there. The telescope's moving all around, but look, perfectly fine because we're only taking the good frames. I think that's pretty cool.
Mark, may I ask a question?
Yeah.
What is what is the maximum that you can adjust for wind before the pictures are no good?
Oh, that's determined by this number right here. Right now I'm set at 9.22. Okay? If I raise it to 11 or 12, and it depends how high up the telescope is pointing. If it's on the celestial equator, we adjust it to be a little bigger because the errors tend to mount up there. So we make it a little bigger. When it's pointing near the pole, the adjustment errors can be much, much smaller. So we can lower that number. So it depends on this number. Right now, with tonight, if we zoom in and look at the stars, okay, we can see that our stars here are a little bit elongated. Okay, and it's because I'm at a setting of over 9. If I set it to like 8 or 7 or less, then we'll be literally perfect. They'll be perfect round blobs. Okay, and there's a black band you see down here. That black band is the error correction that the telescope is going through to prevent the error. So the error is happening in the up-down direction, but it's accounting for it. All right. Again, this has a guide scope on it, which you can't see. It's on the other side right now. And that guide scope is locking onto a guide star and then guiding on the sky. So we're good. So we have 31 here, and I'm going to change the name of it, and I'm going to give it its name. This is the Little Beehive. And the big beehive is a bigger version of this, and that is in the constellation of Cancer. And maybe we can go there next and check that out. So what I'll do now is I'll save this. And what that does is it saves the file. That's an astronomical file format called FITS. All right. But don't worry, you don't need to know what that is. I'll tell you, though, if you want. And then I'm going to save it exactly as seen. So what you'll get is this exact image that you see right in front of you has now been saved as a PNG or a PNG, kind of like a JPEG, but without the noise that a JPEG has. And these are now being shipped out of this observatory 2,500 miles away out in the desert from where I am, shipped up to satellites, and then taken back down where they end up. They end up in our server, and the server is accessible by going to our website. It's our portal, and that's right here, right? SkyTourLive.org. You see that up there? SkyTourLive.org is our portal to everything we do. If you just visit SkyTourLive.org, you can go to our Patreon. You can go and join us. We'd love to have you in the Patreon. And you can also scroll down and you'll see an entry that says, "Take me to cool pictures." And you end up on our server. And the instructions are there for how to get these cool pictures. And you could take them down to your computer as much as you want. Put them out as your backdrops, as your wallpaper. We do get some really, really cool things, you know. So I have a feeling that people will really enjoy these. Okay. Cosmic Ray asks, will there be spectroscopy on any scope? Spectroscopy is the science of disassembling the light we're getting from the stars into its component colors. Because when you do that with a star, you find that there's interesting lines in the spectra of these stars, and they're called absorption lines most of the time, and sometimes there's emission lines in them, and they're like bright line. They call it a bright line spectrum too, but the absorption lines are like dark bands, and this shows us the chemical makeup of a star. That's how we know what these stars are made of. So when we look at these stars and we look at a spectrum, and we look at a spectrum of like some of these stars that are in here, if we find a star whose spectrum is not at all like the other stars, then we know that it's a star that just happens to be in the same field, but might be way up in front or way in the back or just moving through, okay, and not a star that was born in the cluster. So we can identify cluster members by looking at the spectra of these guys here. If the spectrum is the same, they were all born together. Isn't that cool? That's kind of how that works.
Amazing.
All right, so this, we're done with this one. So I'm going to...
Absolutely gorgeous.
We're going to come out of here and go back to our live feed view, okay, which is right here. And then I can do that. And now I can zoom back in here. All right. Now let's go over here, and as I mentioned, we could go, and I think we're going to do it. Can I do that? Will I be able to see it? Yeah, I think so. Okay. I want to show you the beehive cluster, and let me just make sure that it's not too low behind the roof line of our observatory. The altitude should be... altitude is, oh yeah, we're good, 51. So I will tell us to go there now, and now you'll see the telescope moving. There it goes, and there you see it. Oh, hello, Dingo. My dog came in to say hi.
Oh,
all right, and now the beehive will come in, and there it is. And you'll see this is why that other one was called the little beehive, because this is the big beehive. Yeah. It's also known by its other name, Persepi, you know. And some people I did say hi to. In fact, I had one person saying hello from Connecticut. And I want to go back to that so I can find that person and say hello. Because I don't know who that was, and I wanted to say hello to them. let's see. I'm moving back here. Okay. Cosmic Ray, you're on fire tonight.
Right?
Yeah. I think.
He has a lot of good information.
Yeah. No, he's good about that. Just don't get him started on another topic because then he's impossible. Okay.
Oh, it's too far back for me. Let me see.
That's all right. I'm looking for. I think it was Arbiter. I think Arbiter was a Connecticut guy, and I'm in Connecticut running this. But I see we have Rascally Rabbit is with us tonight, and we have, in addition, people. I mentioned Izabela, but I always mention Izabela, and I'll never stop it because she's great.
Oh yeah,
she's amazing. Yeah.
I love it. Like every time I post, like remember to like and subscribe, please, guys.
Yeah.
She follows up right behind me with the Patreon link.
Yeah. Okay.
Amazing. Great help.
Yeah. Yeah. In fact, she was just telling me that your volume is a little low, which is good. I fixed it. Thank you.
Yeah, that's fine.
Thank you, Isabel. Okay, Renee Cruz is with us. Maria Wilson, nice to see you. And
hey, Nova Scotia.
Yeah, Nova Scotia.
Nice.
Stan from Two Rivers Observatories. There you go.
So many Nova Scotia.
Yeah, we do. It's name escapes me. Not Justin.
Okay.
Oh, Jared.
Jared.
Okay, Ronald is here. Ert Radio. Hi, Ronald. I'm just still looking through here. And the Goblin. See, the Goblin won a pair of your binoculars.
Oh, he's here. Right on.
That's right. Sam S.
Good to see you.
Science Bob. That's Science Bob McGuire. Hey, Bob. How are you? I was just watching a documentary that I was in, and the director sent it to me, Bob. And Admiral Tim Gallaudet was referencing the USS Hampton incident on the heels of the incident that I had with an unknown submerged object as well.
Right.
So Tim was talking about that. He was referencing but he couldn't remember your name, so he didn't give your name. I just watched it tonight because Darcy Ware, the director, sent it to me.
Okay.
It will be played out at Contact in the Desert, by the way, Sunday night. I believe at 6 or 6:30 in the evening. And
okay.
I'll be there. I'll make some remarks. Really cool. Renee Cruz, how are you? Let me get this going here because this is.
Ronald, I thought I knew that voice. Hi, Ronald.
That's Ronald. Ronald knows you.
Yeah. He's like, earlier he was like, that doesn't sound like Daryl.
Yeah, I know. Yeah. Okay, I am going to pull this over a little bit, like I said.
Oh, Science Bob. I was on the Hampton in 1990.
Yeah, the USS Hampton, that's right.
Yes.
Tim Gallaudet was talking about that. Admiral Tim Gallaudet was talking about that. I've talked to Tim. He's a really good guy. He's retired now. He started a private sector job, Navy job. Really cool,
okay.
yeah. And Bob had a USO encounter that he said, and Tim knows about them. And he talked about a USO data, a USO set of data that he has that's currently in the hands of a Navy contractor that he would not name because he can't.
Understood.
And, so it was interesting to hear what they're doing with it. They're actually going to try and figure this stuff out. I was on the boat as a visitor. I wasn't even a sailor. Never happened. I got seasick, so that tells you how well I did. Okay. But something came roaring through the sonar at several hundred knots. Okay, that's several hundred miles an hour. Okay, and
That's
it is, and underwater. Okay, so we think about things moving through the water fast, and we think of all kinds of weird, effects. The high heating that would occur when you move something that fast. the noise associated with it. Yet these things are almost silent and move extremely high speeds without even disturbing the water. You know, I think it's really important to understand something, and that is that they don't operate in the 4 dimensions that we consider. That, you know, it's the X, Y, and Z moving through time. They operate in a 5th dimension and in the 4th dimension, and that shifting into the 5th dimension is something that's accomplished with a high source of gravity. Okay, and that's where the Kaluza-Klein hypothesis or Kaluza-Klein gravitons come in. I'll be doing that lecture in Arkansas in April, and then I'll be touching on it again at Contact in the Desert, and then discussing something else at Roswell. I'm doing SkyTour live streams at not doing them in April because the internet down in Arkansas at that location is actually kind of poor.
Oh.
Yeah, that's all right. So, but I will be doing a live SkyTour live stream out in Palm Springs or Indian Wells at Contact. And for those that don't remember, we will be giving away equipment to attendees. All attendees will get a raffle ticket, and that raffle ticket will be drawn before you leave the room. And someone's going to walk out. Actually, Michael and Tiffany can tell us how many giveaways there are going to be in total for our SkyTour events.
So in total for the entire event, we're bringing along 3 pairs of binoculars, which actually we just got received in the mail today, and 2 of the Celestron Star 6 Explorer telescopes, which we're going to purchase very soon.
Excellent.
Well before the event, and possibly, maybe if I can talk Tiffany into it, maybe a 3rd telescope, maybe.
Wow.
Right? She's like, no. We got bills, man.
Well, then maybe instead, maybe another pair of binoculars, maybe.
Who's an adult?
I don't know.
Okay.
Not one.
Maybe another pair of binoculars then, if you're going to squeeze something else out there, why not do that?
Telescope.
That's fine.
Binoculars, we could squeeze another pair of binoculars.
Well,
oh, speaking of which,
yeah.
One moment, please.
Oh, are we going to see them?
I think so.
Oh.
Oh, yes, we are.
And
With
I'm gonna
background
feel like
music.
a little bit like Vanna White. Oh yeah.
All right, well, I'm gonna pull you up on the screen, and I'm going to make you bigger.
Oh.
There, now you're giant on the screen. Look at that. 7 by
This would be the
50s.
Celestron that we will be giving away. These are amazing binoculars.
Excellent.
They're very lightweight. I'm a short guy. I'm only 5'8", and my hands aren't that big at all. So as you can see, even my small hands can hold these amazing binoculars.
And they come in a cardboard box.
And she has even smaller hands. Check this out. There you go.
And they're within that. That box is just the container.
It's, very lightweight.
Very nice.
Very light. Very easy to handle. Very easy to operate. And in the future, we're also going to be offering the for you, those of you that wish to record what you see.
Ah, yes.
We're going to offer, along with this, will be on the stream as well. As we give away these on the stream on SkyTour live, we'll offer these, but we will also offer the Celestron cell phone attachment, so you can attach it. If I can get a good photo here, yeah, you can attach your cell phone to that eyepiece right there, and record, take pictures of the night sky with ease.
Very nice.
Absolutely.
Very nice.
So that's what we're doing in the future.
Wow. And that's not all. There's a lot more, by the way. But we're talking about offering a Aurora Sport night vision system down the line to people, and we're talking about different types of binoculars that might be better for folks. So we got a lot planned, And,
Oh,
and
yeah.
it's all courtesy of those two right there. Those two folks right there. See them?
Courtesy of
We got
SkyTour live stream.
Bing, bing, bing. Yep. Yeah. So they're actually very good folks. So you know what, Mike and Tiffany were those science educators that some of us had in our elementary school days that were just so dedicated that they would stay after late. They would take you
Yes.
on field trips. You'd go looking
Yes.
at the night sky in a school bus with a bunch of kids, and that's what these guys are. They were born in the wrong era, or actually maybe the right era, maybe the right
Yeah.
era.
I agree. Where's my horse and buggy?
Yeah. So,
My night
so
sky.
show them some love. They're doing an awful lot for a lot of people, not just SkyTour. They're doing an awful lot for people who want to learn about the night sky. And we'll talk also about the night sky project that you'd like to see, a network of telescopes and binoculars and observers. It's really the network of observers.
Hi, absolutely.
That's another thing. I do want to say hi to Mr. Django he's over in Belgium. Okay.
Yes, sir.
And there's Arbiter 569. Thank you, man. That's great. Yeah, very cool things coming out from Celestron soon. See what he says?
Yep.
Yeah.
Yeah,
Arbiter,
yes,
where
sir.
are you in Connecticut? Because I'm in Terryville, Connecticut, in our little observation bunker here where we run the telescope out in Arizona.
Science Bob has 2 psionics. Got the Aurora Sport and the Osprey.
Nice.
I would love to hear a what do you think about both, please? Because we are definitely going to be giving those away soon as
Yeah,
well.
that's the night vision, the Aurora Sport.
And that's a monocular that will also be easier set up with the cell phone attachment.
Yeah.
So you can hook up your cell phone
Yeah.
camera to.
Actually, you don't even need that because it does Wi-Fi transmission because it generates a Wi-Fi signal, and you
To your phone.
you connect to it with your phone, and you can record the video just like that if you want to as well. So it's very
That's
nice.
amazing.
Yeah, you don't have to hook it up to anything. You just tell it to do that.
That I did not know. That's
Yeah.
amazing.
Mr. Django says beautiful binoculars. See that? He was watching.
Oh.
He's watching.
Right on.
Yeah, no. See, we have a great SkyTour family. Everybody's great. So here is the Beehive cluster, right? And as you can see, even looking that high in the sky, the wind appears to be calming down because we went from having an equal number of frames that were bad, 21 to 21. Well, now we're winning the game, 22 to 1. Not bad. All right, so I got it set up there. I'll save it. Okay. I can't believe we weren't disturbed by a satellite going through here. Those Starlink satellites.
It's all my fault.
Michael works at Starlink, guys. He works for SpaceX. Yeah. So we're
Astronomers hate me.
actually no. I mean, this astronomer doesn't because without it, we'd have a tough time. We were broadcasting with the Viasat or HughesNet earlier in the beginning, and everything I did there was a 3-second delay. I literally had to program myself like a music conductor, conducting an orchestra, to click and then know what's coming to then anticipate the next move. It was an
Wow,
awful
that's-
lot of thought.
Yeah, that's awful.
Yeah.
This is very. You get pretty good upload and download speeds as well as low latency, extremely low latency because of the distance of the Starlink satellites themselves.
Yeah, that's right.
They're very low Earth orbit.
Yeah, and HughesNet and Viasat were at obviously geosynchronous locations, so they have a noticeable delay of time for the signal to get here.
Yeah.
Arbiter's in Bloomfield. I worked in Bloomfield for years. Nice, fan. That's good to see you. Yeah. All right. So, all right. Okay, so the Beehive, it says cosmic rays. Here's an example. That's what I'm telling you. Look at STLS is observing Earth tonight and giving away Glock Zibbeldink. Wow.
Sorry for the phone drop, but that was hilarious.
That's the equivalent of a mic drop.
Mic
Man, don't you
drop.
fall. You already had your mic drop. Don't do it again.
I did. I don't need another one.
Science Papa's answers your question, by the way. And Mike did share with me earlier that the SpaceX launch was scrubbed for today.
Yes, that was the SpaceX launch tonight was actually with Dragon atop
Yeah,
it. We were sending Crew 8 to the ISS, and it was scrubbed for this evening. We wanted to bring it to you guys live because actually it was supposed to happen around 11:15. In the next 45 minutes, it would have been launching.
Yeah.
But they scrubbed it for tomorrow, unfortunately, and hopefully we can get those guys up there tomorrow because they have a lot to do. There's like over 200 experiments that they had planned or have planned aboard the ISS.
Yeah. Well, we would have cut over to it and run that to show folks here. Then after it launched, we would have actually then come back and done more of this. Okay. So,
We hope to bring. That would be amazing if we could bring launches. As we're doing this, we could bring the launches. We could all watch it together and feel that energy when those launches happen, especially when we're launching astronauts into space. There's nothing like watching a Falcon 9 launch and just feeling that excitement.
I want a field trip down to the 3 mile watch limit and just that'd be great.
I can go down to Boca Chica and actually go on site. Use my SpaceX credential. I could. I don't know if I can get you on there though because you're not. Oh, she's upset about that.
You know what? I'll call Elon and let him know. I'll tell you what's funny. Okay, this is another cluster we're looking at here, which is really interesting. And if you notice something, this is a cluster that actually looks like something you know. It's called the 37 cluster. Does that not look like a 3?
Oh,
and a 7?
3, 7. That is really cool.
Yeah.
The universe is crazy.
Yeah.
That's beautiful.
Yeah.
Hey, I'm 37.
You are 37.
So this is for you, Tiff. This is the 37 cluster. From now on, we're going to call it the Tiffany's what? Gotta have another T in there. Tiffany's something. Tiffany's. I don't know. Yeah. Gotta keep it clean, though, obviously.
Yeah.
Okay, so we're gonna just head to the east a little bit here. All right, so this is Tiffany's cluster.
There you go. That's pretty cool, actually.
Yeah.
That's definitely.
I went the wrong way. It's the other west. Yeah, and so we'll take a quick picture.
The other west.
I went the other. Yeah, I went the other west. Yeah. Yeah.
Oh my gosh.
So there we are.
It's her favorite cluster.
Well, it is now, isn't it?
Yeah, right?
Okay, and there is our center, so we're good there. Okay, so we're really close. So now what we can do is set up an exposure. And, again, for the record, I just want to show you, the two most important fields in all these here is this one, right? This is the exposure field, right? And then the gain. So this is the sensitivity of the sensor. It's set to 250 right now. And this is the exposure, the amount of seconds that we will expose that gain to light coming in. So that's what this does. And you play with the different values until you get an optimum setup. Okay. And so now with Tiffany's cluster here, we're gonna do another 12-second shot. Here we go.
Sorry, Maria says Tiffany's Twinkies.
Yeah.
Because they twinkle, right?
Yeah.
Twinkles.
Yes. Yeah.
I need better glasses, apparently.
These are Tiffany's Twinkles, which
Twinkles.
that could still be something kind of off color. We'll just let that go.
It still can be off color.
It could, but it's all right. It's fine. Tiffany's twinkling.
Twinkling.
Okay. Oh,
Yeah.
hang on. All right, let me. I gotta do a couple things here. First things first. I gotta
Okay.
remove this extra histogram, and I have to clear this and let this do this again. And of course, we have to wait for your Starlink to show up again. There we go. Okay, and now the next image will come in if we get it now, which should. There we go. There we got an image. All right, look at that.
Wow. Look at the color shift.
Yeah, it's really pretty. Actually, let me color correct. Okay,
Okay.
so you watch these red, green, and blue curves. They're actually quite close to being aligned right now, but I'll do it anyway. All right, and you can see that now. And then this one will give us a little processing. That's a starting point, and then I can actually maneuver this and pull it to the edge of the curve. This is the black level, and you want to ride up this curve where the data starts, and just before the top of the curve, that's where the maximum darkness will be, okay, without losing data. If you go past the top of the curve, now the faint stars are going to start disappearing,
Yeah.
okay, and then you're going to lose some of the brighter ones. Of course, it looks really pretty, but that's the kind of picture you might take with a camera that's just like a regular telephoto. If you then use a telescope, then you're going to get all these other stars in here as well. So there's a lot to go on there, you know.
There are so many stars.
Yeah.
It's
Yep.
not even fathomable at all.
And
How many?
Izabela, thank you for putting up the links to these up there. She's putting up the links for everything. And Poison Arrow Frog is with us. Hey, man, how you doing? Good to see you.
Oh, Blues Traveler, Tiffany's Candles,
Oh.
TC.
Oh, yeah, Tiffany's Candle. That's nice. Yeah. So from now on, this is going to be called Tiffany's Twinkling Candles.
Just until next year.
Oh.
Yeah, there's no 38 cluster, guys. I'm sorry. All right. While this is still coming in, we got 9 frames, and they all have survived. Let's take a look at something else to look at here. I know there's a lot to see in this area. We're way past the meridian. Let's see if we can zoom in here. And would it be that? I don't think that's figure its altitude. Yeah, we can see that too. Okay, so we'll come back to that in a second because we are right there, so we're actually pretty close. Now, we're going to go to another object here. I'm going to save this with a 12. Very good, 12. 12 exposures stacked. And that gets rid of the more you stack, the more noise gets removed from the image. You know, so it's pretty cool. By the way, hi Blues Traveler. I heard them say it. I even said it. And I didn't say hi to you. Okay, there we go. And now this image will be sent up, and you can bring them down and enjoy them and explore them. I also want to point out that Izabela's been doing some real science with our data. She has found objects that look like stars that in subsequent exposures are no longer there. So she discovered an asteroid that's moving through the Pleiades, for instance, and an asteroid that's moving in another location in space. Now, they were identifiable asteroids, and she managed to find out the identities of the asteroids. In one case, she saw an asteroid, and then later on, in a different exposure, saw that it had moved elsewhere in the frame, which is really, really cool. She says, well, sort of real science. No, real science, okay? Look at, it's how Clyde Tombaugh found Pluto, okay? Mm-hmm. Using the techniques you're using. He just used a very simple blink comparator, and you are using Photoshop, you know, and a program I think that I wrote, I think you're using that too. I wrote a program to actually give you distances and measure distances and so forth in a frame, and then know how far away it is, and how far away it's separated in real life.
That's right. That's right. Isabella says, very cool indeed. It's so great to see the universe in motion. It is amazing. And for you to find such artifacts out there, that's incredible.
Yeah.
So you are doing, read my text. Don't sell yourself short. You're doing real science.
Yeah, she is. And of course, Cosmic Ray, he says, oh, this is up for the Knoebel Prize from the Knoebels Amusement Park in Pennsylvania. Yeah, very nice there, Cosmic Ray. Very nice. Very, very nice. Uh-huh. Yeah, and Science Bob says something that I've mentioned a lot of times, and that is our computers are great blink comparators. What's a blink comparator? Well, let's say you take a photo of the 37 cluster, and let's say you take another photo in 6 months. You align those photos together, and then you blink. This one, that one, this one, that one. And you can, if you do it fast enough at a nice rate, you can look around and scan the image and see if there's something that wasn't there that shows up in one image and not the other. You can also see movement of objects. That's how we did that with Barnard's star. It's one of the closest stars to us, around 6 light years or so, I think. And over a period of 3 months, we saw it move in the night sky because Barnard's star, being so close to us, moves quite a distance in our sky over a short period of time. So it shows you that the universe is a very dynamic place, and that's what that was all about. Okay, so 37 cluster will be saved one last time, and then we will save it exactly as we see it, and then move on to the next item up for bids on The Price is Right. All right, let's do this. All right. So, Mike, when we're out at Contact,
Okay.
I'm going to be doing a workshop. I'm going to be doing an intensive, they're called, and I'm also going to be working with Ben Hansen on his Skywatch. Ben Hansen and I are good friends, and they asked if I wanted to do work with Ben, and I said, yeah. I called Ben. Ben, you want to do? Oh, yeah. So we're going to work together, and so I'll do an astronomy segment for him when he's talking about the night vision equipment and using tools to look at what things are in the sky that relate to aircraft. He's a airplane pilot, so he's very, very capable. So that'll be a lot of fun. Very interesting stuff. Yeah.
For Ben Hansen, that's actually the people that are attending that workshop or intensive or event, I should say. They're all going to be bussed out to away from all the light pollution that the actual event. There's a lot of light, but again, it's a resort and spa, so it's lit up very beautifully. However, it does interfere with Skywatch, a really good.
Yeah, listen to the guy from Starlink saying it's lit up very beautifully. Okay, lit up and beautifully.
Lit up beautifully. I love that place.
Lit up and beautifully don't go together. I know, I'm kidding. Well, I'm sort of kidding. No, I'm not kidding at all, actually.
No, you shouldn't be. No.
All right.
Astronomers don't light.
Okay.
Light pollution is not
It's
good.
garbage.
Yes, exactly.
It is terrible, yeah. Okay, we're moving a short distance right now. The telescope, which is here, we're going to go right over here, and we're going to look at another object that is right there. And this one is a fascinating object because it is the remnant of a star that has blown itself up entirely.
Oh.
Yep. And this is a supernova right here that you're going to see in just a moment.
You see that?
Yeah.
Mm-hmm. Well, you'll see it a lot better. Okay, in just a minute, yeah. So it's called the Crab Nebula. It is the first in the list of Messier objects that Charles Messier found. And Messier 1 is several thousand light years away. and it is like I said, a remnant of an object that was seen in the sky in 1054 AD by Chinese astronomers. It was in the daytime sky. You could see the star during the day. Okay? And that's because it was so bright. Now, like Betelgeuse, this star was probably we know it was a red supergiant, and it went supernova. And the reason supernovas occur is it's sort of a dense topic, but I can just sort of summarize. A star uses hydrogen fuel initially when it's first made, because hydrogen is the most plentiful element in the entire universe. And so it uses hydrogen and fuses it into helium. And when it does that, we're doing a 24-second shot here, so I'm going to get out of our histogram, go into our live stack, and clear the last one if I have to. The 37 cluster, Tiffany's cluster. Okay. And then we'll hopefully see this one come in. All right. And you'll see the supernova. There it is. It's going to be here. There we are. Boom. Okay. So,
wow.
So this object, okay, again, seen 1054 AD in the daytime sky, and then it faded from view. This is the remnant of a star that had run out of hydrogen fuel, and then it was using helium fuel at one point and fusing that into carbon. Carbon was being fused into nitrogen, oxygen, and so forth. And it went all the way down the periodic table. This is where our elements come from that you're made of. It comes from these guys. It comes from the hearts of the stars. And so in this particular object, when you look at the spectrum, in other words, when you break up the light that we see here, and you look at what's inside, what it's made of, you can see that it has an awful lot of elements from our periodic table that you'd be familiar with, because the elements that you make you up come from all these supernovae that have occurred. All right, so we're waiting now for more frames to come in here. Now, what's interesting about these supernovae is that when they finally get to iron, which is number 26 in the periodic table, when they finally get to iron takes more energy to fuse than it gives back. So it's a logical stopping point in stars, and it becomes this like sand in your throat. It becomes an irritation to the star. Mm-hmm. And so then around that iron core, other shells of these previously fusing elements are going through their process and fusing. And the last one to fuse is silicon. And when silicon fuses in the heart of a star, it lasts for only 1 day.
Wow.
Oh.
1 day. And then after that, it can't handle it anymore. And so what will happen is the star's core begins to collapse. All those shells collapse because it's no longer fusing enough to support the massive star's gravity trying to crush it. Okay?
Right.
Because that outward flow of radiation, like pushing out at very, very high speed, okay, that can't actually support the crush of gravity anymore. So what will happen is the star will end up collapsing in its core. As it collapses in its core, this liberates through a series of processes particles called neutrinos. And the neutrinos race for the surface of the star. And only 1 in 1 billion neutrinos actually gets out, because it's very dense in there and it's colliding with all kinds of stuff, but one of them gets out. And because we see a huge flux or flow, if you will, of neutrinos, we know that a supernova is underway or is going on. But if you looked at the star that you saw the neutrinos coming from, it would look perfectly normal for a period of time. Now, these are supergiants. Now, Betelgeuse, if you put it where the sun is, would be as big as the orbit of Jupiter. Okay.
Wow.
So it'd be 10 astronomical units in diameter. That roughly. So that means that it's massive. So neutrinos travel at the speed of light, but the supernova, when it's occurring, it's a shock wave of destruction moving out from the inside of the star. That's not moving at the speed of light. That's particles and material, physical stuff moving. It can't even get close to the speed of light. So the stuff that comes out of that star, okay, the neutrinos come out first, and they stream out all over the star. And finally, if we see it, we have a few hours with a star like Betelgeuse, and we can say, hey, neutrinos coming from Betelgeuse. It's going supernova. Point all the telescopes in the world at it. And then
So it's
a precursor. It's actually, the supernova's already happening when we see the neutrinos. Okay, and by that time, these neutrinos, as the herald of a supernova, would warn us, and we'd be able to turn the telescopes. And maybe with Betelgeuse, the amount of time it takes for physical material to go out to like the orbit of Jupiter,
right,
could be hours, if not days. So by the time it gets out there, we've already had plenty of time to start observations of Betelgeuse and start going through the process. If we see the neutrinos, most likely we're just going to see this bright new star in our sky. If Orion's on the other side of the sun, that is, we're going around the sun, and so Orion is going to be near the sun during the daytime, and we'll see a new star in the sky, and that'll be Betelgeuse. So we'll see what the Chinese astronomers saw when they saw this guy right here that we're looking at right now.
I hope it happens within our lifetime.
Oh, I know, me too. Now, Betelgeuse is anywhere between 5 and 750 light years away.
Right.
Okay, just a second here.
Okay.
I do not understand that, but it'll come back.
Oh, did we lose the stream?
Yeah, but it's back. So I just have to.
Oh.
So let me bring you back too, because you don't have connection anymore to this. I'll give it to you.
Okay.
This happens from time to time, and it's
no
not a Starlink thing. It's actually a
RAM thing.
no, not at all. It's actually an internet breakdown between here and Arizona.
Oh, understood.
And
okay.
since it's momentary, we're okay.
Oh, good deal.
Yep. And those of you here, make sure you read Cosmic Ray's stuff. He contributes nicely when he's not harassing everybody.
He's got a
Ray.
I've been reading a lot of.
We like you, Ray.
Absolutely.
We like you, Ray. Carl Becker is here, first time. Hey, Carl, how you doing, man? Adam Parker, how are you guys? Thanks for coming in. And you know what? If you guys aren't members, please subscribe. Because we want to be able to have more telescopes to show people things. We're building a solar observatory out here in the East Coast. We're building another observatory out in Arizona. We actually have some donations for that one. But join our Patreon, And also, one of the things you could do, which I think might be kind of fun, and you can ask members in the chat who've already done this, you might want to consider going here to our Etsy store. We actually have a store where we have actually been able to let me get it to come up here. We've actually been able to create these pictures and then put them on amazing things like mouse pads and mugs and bedspreads and blankets and shoes. I have a pair of bedspreads. I have a pair of sneakers with a horsehead nebula on. It's really pretty.
What?
I do.
Wait.
He had
Now I
shoes
have
last year at Contact.
If
on
I
his
sent
booth,
you
at
a
his booth.
pair of like pure white Adidas shell tops.
Well, actually,
Can you have?
No, see, we actually have those made. The sneakers are made and they're printed.
Excuse me.
Yeah. We have playing cards, we have mouse pads, we have mugs. You want a wrap for your car? Yeah, we don't have that, but
Oh. Yeah, right. Our ears perked up.
a wrap for your car? Yeah, no. No, we're actually we want to, as part of the long-term goal of SkyTour Livestream, we want to build a mobile observatory that we take to cities and towns across the United States, college campuses. Is the plural of campus campi? Okay, and we want to do that as well, and that would depend on some serious grants and so forth. But that's okay. We've had a couple, or one grant at least, come in that was nice. It was a great grant to get, and we've applied for a couple others. So I don't know if we'll get it, but the Patreon helps keep us paying the internet bills. We have, like I said, Starlink, and we're going to have 3 sites, and it's going to be $120 a month at each site. So that is we want to be able to make sure we can cover that internet. And again, I hope that the folks that are just joining us choose to stick around and hang with us, because there's so much to see. Let me show you something here. What I'm going to do is I'm going to zoom in on this, all right? And when I zoom in, all right, you gotta let it come in here. I want to show you in the center. Do you see that little dot right there in the middle? Okay, let me see if let me reduce the noise in here. So this will be instant reduction. Boom, that looks much better. And then let's actually sharpen up these details. Okay, so now you see that object right there, and if you don't see it, let me outline it for you. Okay, the object I'm pointing at right now is right here. It's in that red box. Do you see that little dot in there?
Yes.
That's a remnant of the star that created this supernova.
Wow.
And that's actually called a neutron star, but it's a special kind of neutron star. It has hot spots on it, and it's rotating very fast. Now, stars rotate. The sun rotates, leisurely, once a month approximately. This star, as a remnant of a massive cataclysmic explosion, rotates every second 33 times.
What?
Oh.
Wow.
And it's not the fastest rotating neutron star.
And it's not the fastest.
No. And by the way, how big is the neutron star? Well, the neutron star is about the size of Manhattan Island.
Oh.
And this is thousands of light years away, and you can still see it. That's
Right.
how energetic it is. So think about that. Isn't that crazy?
That is
Right.
Yeah, it's not even fathomable.
I know. I know.
Wow.
Sure.
Wow.
Yeah.
33 times every second.
Yes.
Mm-hmm.
Yeah. Yeah. And that is the neutron star. You'll notice, if I can zoom in a little more, let me first come back to this. If I zoom in a little more, we might be able to see that the color of this neutron star, you can actually kind of see it's a little more blue than the rest of the stars. It's a bluish color. Okay. Neutron stars are very, very hot, so you can see it's got a little blue tint to it.
Yeah.
Yeah. Let's turn off.
Wow.
Let's turn off our sharpening for just a minute.
Seeing this on the big screen is just incredible.
Oh, you got it up on your big screen?
We have it on our 42.
Oh, okay.
And literally, like, the nebula as a whole is like this. The star is like this.
Oh,
in
that's
our
cool.
screen. It's amazing.
Yeah.
That's wow.
Yeah.
And all of this outer layer here has been growing since the 11th century or the 9th century, right?
Yeah, 105480, and
so that's the 9th century.
And only in the last 100 years have we been able to photograph it, right? 150 years. So
really,
because cameras, And
okay.
So
yeah.
once they were invented, once we had cameras, they started immediately photographing this. And it's been photographed for well over 100 and something years, 100 and some odd years. And what they've done is they've assembled that into a time lapse, and you can literally watch this expanding outward. It's absolutely incredible. So, yeah, the universe is dynamic. The universe is always changing. The universe is not static. You
Right.
know. Now, here's the thing.
It's so incredible.
You see these colors. These colors are very representative of what's going on in the universe too, because you remember I talked about the spectra. The spectrum,
Yes.
break the light up into its component colors. Well, sometimes when you have a spectrum of a star, you'll see these dark bands. These dark bands are called absorption lines. And that's when hot starlight in the core is going through relatively cooler gas outside, and that cooler gas absorbs a little energy. And that absorption shows up at certain places in the spectrum. And those places are very specific for very specific elements. Okay? So then you have another kind of spectrum that I call the bright line spectrum, where when you look at an object like this, you see that it's glowing green and it's glowing red.
Right.
Well, that glow is the opposite kind. It's actually a very hot gas, and the hot gas is emanating light in specific locations in its spectrum. And when you look at the spectrum, you'll see bright lines. Okay? So you
see-
have, when you see bright nebulae like this, these are emission nebulae. Okay? Orion's Nebula is an emission nebula. Okay?
Right.
This red color is due to a specific element going through a specific process, and it's hydrogen. Okay?
Yeah.
The hydrogen electron, which is around the proton, right? The hydrogen electron is ionized by the hot neutron star's radiation, and it jumps off the atom for a period of time. Right. So now to do that, it absorbs energy and climbs to ever higher orbits until it's free of the atom. But then it's colliding with other things out there and falls back into the atom. And as it falls back into the atom, it gives up that energy that it gained when it left. And in the hydrogen atom case, the light that it gives off is red. And that's
Right,
called
okay.
hydrogen alpha. And this green is another element doing the same thing with two of its electrons. And this element is oxygen.
Oxygen.
All right, so this is
Incredible.
singly ionized hydrogen gas glowing red, and this is doubly ionized oxygen glowing green.
That's absolutely
It
incredible.
is. It's just incredible, you know. So
And oxygen is the third most common isotope in the universe.
element,
right?
yes. Everything
Element.
you said was correct, except it's not an isotope. It's the element. Yeah,
Isotope.
yeah. And carbon is the fourth.
Carbon being the
Yeah,
fourth. Okay.
so it stands to reason that life in the universe is based on carbon because it's the
Everywhere.
fourth most abundant element. You know,
I've heard theories in regards to like silica or silicone.
silicon. Yeah,
Is that what is that all about? Like
Yeah.
silica based
silicon-based life. Yeah. Okay. The reason
Mhm.
reason people thought that goes to the periodic table again. When we look at the periodic table, okay,
Okay.
you have carbon, and then in that column right below carbon is silicon. Okay, the columns in the periodic table are the atoms that are kind of most like each other. So under carbon, okay, you notice next to carbon is nitrogen. Well, nitrogen and carbon don't
Sure.
have any properties in common at all. So
Right.
it's the vertical alignment that makes the difference. So carbon is close to silicon in a variety of chemical characteristics, elemental characteristics. But the thing about that column is those are the most like elements. So the next likely element that would cause or provide a stable foundation for life is potentially silicon. And that's why people say, what about silicon-based life?
Aye.
Well,
Interesting.
unfortunately, silicon...
Oh, here's the bad news.
Yeah, here's the bad news. And below silicon, you have others which are less capable entirely. It's less capable from carbon on down. But
Okay.
the thing with carbon and silicon is carbon is an atom that has four little spots on the outside of it that can bond with things. They're called, for those in chemistry out there, valence electrons. Okay,
Right.
well, those available or valence electrons are electrons that can bond with and make and break bonds very easily with literally hundreds of thousands of different elements in combination. So
Okay.
that means that we have the greatest opportunity and flexibility with the carbon atom. Now we go to silicon. Well, silicon has some availability too. However, the problem with silicon is that it tends to make crystalline lattice type bonds. So we find that silicon bonds are very tenacious. They're not easy to break. So you can't take a pill based on silicon and expect it to break apart in your stomach and provide you with a drug that is going to help you. You're going to end up with a knot of dirt in your belly. Okay, it's kind of what it comes out to be, silicon. So silicon is too robust. When it makes bonds, it doesn't like to break them, and to break them, it requires an awful lot of energy. Witness a meteor entering into the atmosphere. Many times, it's a little piece of iron or a piece of silicon, and it's literally the size of a grain of sand. Yet here from the ground, when it goes into the atmosphere, it burns up, and it's so bright you see it with your eyes 100 miles away. You can see a grain of sand, okay, burning up in the atmosphere. So that's because it's moving fast, and that's because the energy is ripping apart the atmosphere. The frictional energy from its kinetic energy, the energy of motion, is ripping the sand grain apart and ripping apart the oxygen atoms that may be tied to a silicon atom. Okay, or it can be ripping apart the silicon structures that are all silicon atoms or iron, etc. Okay, now, interesting thing is when you walk on a beach, okay, to see the tenacity of these bonds, you stomp your feet in the sand, you're stepping on mostly gas. Because sand is silicon and 2 oxygen atoms. 1 silicon atom, 2 oxygen atoms. So a silicon dioxide is sand. So of a molecule of sand is literally 2/3 oxygen in terms of the count of the atoms, and only 1/3 silicon. Now, yes, silicon atoms are a little bigger. So yes, that's why silicon, you can step on it. But it's kind of cool when you consider that we're looking at mostly gas.
Right. You learn something new every day. I did not know that. That's pretty cool.
All right,
That's definitely.
I'm going to change the name here to Crab Nebula. We'll take one more look, and then we'll move on. That's really pretty.
It is.
Yeah.
Absolutely is. And just awe-inspiring, really, when you think about the level of energy needed to create that.
Oh, yeah.
And how long it took to create that.
Yeah.
It's just... It kind of makes you feel small.
Yeah, it does.
Not lie. It makes you feel pretty small.
Yep. So this is the Crab Nebula right here. You can see these beautiful filaments. Let me... okay, we got the unsharp mask. What I'm going to do is I'm just going to kick that up a little bit. Bring those filaments out. Now you can see a little more detail in here. See all this little detail?
Yeah. Oh, yeah.
Yeah, this is it, man. And the neutron star is now showing a little bit more blue,
Right.
which is nice. So you see oxygen, you see hydrogen emission, you see the beautiful ionized gas that used to be part of the star's envelope, part of what made up
Right.
the star. But it's
Right.
spreading out light years now.
Light years. The distances.
Oh, yeah, and it's going to keep on going
just-
until it's so tenuous you don't see it anymore.
That's just so... yeah, and many, 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 many years, long after we're gone, that thing is still going to be around and expanding and expanding and expanding. Hopefully future generations will continue to record this phenomenon.
Well, they're gonna, obviously, because they're gonna have the history. See, once we started taking photographs, we established a history of being a photo-taking civilization. All right. Obviously, it's like, just look at what people put up on TikTok.
Right.
Yeah.
Right.
So-
That's true.
Yeah. All right, so here's what we're gonna do now. I'm going to save this.
Donald.
What do you-
That's very true.
What do you say?
Really good episode. It says, Donald says, in the Star Trek episode "Devil in the Dark," the Horta was a silicon-based life form that excreted acid to eat through rock, quote unquote, eat.
No
rock.
kill eye.
Yeah, no kill eye.
Cry for the children.
Spock.
Yeah, say, damn it, Jim!
My
I'm beginning to think I can cure a rainy day. And he's got that
Right.
concrete on his hands. I troweled it in there, and
Oh yeah, DeForest Kelly.
Yeah.
Amazing,
Spock.
amazing. Guy.
no, he said, Doctor, you're a healer. Fix it.
Right.
What?
Fix.
Fix it. Fix it, Bones.
Not a stonemason. Cosmic Rays Jim. I'm a doctor, not a stonemason.
Yeah. All right. Cool.
Oh wow.
All right, we're good here. It's good we saved it. It's off, and this is fantastic. Okay. Yeah, so that was a supernova, and we're getting close to that being one of the last times we could view this for the season.
That's right.
No,
Galaxy season
yeah,
coming
he
up.
said,
Yeah.
I'm a doctor, not a bricklayer.
A bricklayer, right?
Bones, you're a healer. Fix it. And he's like, and he goes over there. I love him when he comes over with the concrete on his hands. You know, Jim, I'm thinking I can cure a rainy day.
Right.
No, Bones, you can't cure a rainy day. I'm sorry.
Also, I would like to mention, if you guys are members of our Facebook page, I post a lot of stuff there. Django was mentioning that I had posted the Falcon 9 booster landing, or it was not Falcon 9, excuse me, Falcon Heavy. There was 2 boosters that were landing at the same time. I posted that to our Facebook group page. If you guys are interested in me posting more photos and more video of SpaceX's rocket launches and what have you, I'll gladly do that for you guys. I recently posted on my personal Facebook close-up photos of the 300th launch of our Falcon 9 rocket. And I normally don't really post a lot of stuff anywhere, really, just on my personal Facebook page. But I don't mind posting those type of photos if you guys would like to see those photos.
Of
In the
course
future.
they would.
Right on.
Of course they would. Okay, we are moving now to a special place called the Christmas Tree Cluster. And this is it. I'm going to be moving us up a little higher here.
Just wait.
Yeah.
It's lovely. Absolutely extraordinary.
All right, so now we got to take us up a little higher. I still think it's just an amazing thing to realize the telescope's 2,500 miles away. And if someone was standing there looking at it, they're going like, what in the heck? How's that doing that? You know?
Yeah, right. What was that noise? They're like a few...
Yeah.
Like,
Yeah.
We're being abducted.
What happened? What happened? What happened? What happened, Muskie?
Right?
Yeah. All right. Deputy Dog. Oh, hi, Sheriff. Yeah, so this is the Christmas tree. It's upside down. You can see the base of the tree, and then it comes to a point right here. And right there is a very special nebula. But what I have to do first, what I'm going to do, and I do this periodically in the night, is I'm going to run it through a focus run again and make you all wait. So there. No, I'm gonna run it through a focus run because I want to have perfect stars for this, because there's some small details in here that you just have to see. So this is cool. So kind of fun so far, Mike, or sort of boring?
Oh no, this is I'm answering. I find myself answering a lot of questions.
Yep.
But I would like to continue to, because I'm learning as you go along. I'm learning a lot as well.
Mm-hmm.
So I'm kind of going in between. Well, I'll give you an example. Carl, our new subscriber here, Carl Becker asked how often you guys do live streams.
Oh. Well, that answer is sort of course, weather dependent, Carl. However, it seems to, and Izabela's answering, Mark streams every time on a clear night and when he's available. Yeah, subscribe, set your notifications on, and make sure you drop down that notification dialog and click all notifications. Okay, because I get it. Like I do have real work to do. I do a lot of work for the Navy, so I've got Navy projects I'm working on. But that said, I'm also an astronomer, and the night sky is my cathedral. So to that end, I'm always in church.
Yep.
Right?
Yeah.
Quite the cathedral.
Yeah. Yeah, it's my stellar cathedral. So, and I just find that it's so exciting to just look at something, even when we look at the same thing time and again. Izabela's pointed out why that's valuable, because what we do is, we create these images that you too can see. You can see back a year's worth of data. You can do everything that she's doing right now, because all of our images are up there for you to see. They're all free. Okay, if you join our Patreon and you support us, then you get the highly processed photos that we take, and we remove extraneous noise, and we show you the final product that show detail that is still not even quite visible in these raw shots that we save off here. Okay, but and that's by going to skytourlive.org up there. Okay,
That's right.
right here. Right
there.
And you go to skytourlive.org, and you'll find yourself able to, be part of this magic, I mean, there it is right there. That's me right here. Hey, we are. Hey, right there.
And also, Carl, for future reference, we do hold contests, but they're super random on this live stream itself. We've been speaking about Contact in the Desert and doing contests there. Obviously, those are going to be in-person contests. But however, Tiffany and I also run very randomly, and you never know when we're going to do it. We hold contests in this very live stream.
Yeah, we are the official equipment giveaway outlet for Michael and Tiffany's giveaway project.
SkyTour live streams.
Yeah.
Giveaway project.
and that too.
Yeah.
Okay. All right, we are focused here. So what I'm going to do now is hop out of this and show you what I mean by a beautiful universe just waiting to be seen. Okay, it was Carl Sagan who said, and I'll say it his way, somewhere something amazing is waiting to be known. And he was my favorite astronomer.
Yeah, mine too. He's got it down packed. I'm so trying not to laugh.
Well,
Rest his soul. I love Carl Sagan.
oh yeah.
That's awesome. That was that was very
Well,
close.
I used to do lots of impressions. There was a guy I know had a radio show, and he wanted to go to dinner from 6 to 7 at night. So he'd have me call in and talk to myself for an hour, and I just talked to all these different characters. I mean, I had Popeye talking to Yoda, talking to Darth Vader,
wow.
and going on.
How did that? I would love
Space
to hear
shuttle it is, yes. You are part of a rebel alliance and traitor. I mean, it just goes on and on. Yeah.
They make a pill for that.
Discus Popeye. Hands me goyle.
I mean,
That's nice.
so
That's creepy, actually.
it's creepy.
He channeled Robin Williams.
no.
Chris-
Actually, you know what I used to say?
Yeah.
That all you have to do is be able to imitate Robin Williams' speaking voice, and then you can do all his characters.
Oh yeah. Oh yeah.
Oh, say it isn't true. All right, so this is going to be a 25-second shot here. This is good. Okay, let's see. Waiting for it to come in. There we are. There we are.
Thank you guys. We're getting a lot of laughs right now. Thank you guys so much.
Oh, well, they're good people here.
Hi.
Hey, OG Skywatch is with us. How you doing, man?
Yeah.
Oh, Jack Horkheimer. Yeah. And I remember the song and everything. Jack Horkheimer was a star hustler. Jack Horkheimer, star hustler. And he would do like 6 minutes once a night on certain stations, and he was an astronomer that kind of publicized it. What I want to do is I'm working toward being a kind of like a Bill Nye kind of guy.
Right on. There you go.
Okay.
But with the credentials.
Without the politics, okay? Because I don't,
Yes.
there's scientists
Yeah.
don't talk politics. You just don't do it.
Right.
That's a suicide.
Yeah, exactly. Talk science.
Yeah,
not
science.
politics.
Everybody can enjoy science. You talk politics, it's
Exactly.
50% of the people say you're a jerk. So the heck with it.
Oh, Papa Tom, good night, brother.
Good night, Papa Tom.
Thank you so much for hanging out with us
Yeah.
tonight, man. That's awesome.
Yeah.
He came early. He was here.
He
early.
was. He was.
He was the first one here.
Oh, nice.
Yeah.
Carl Becker says, when I was a teen in the Florida Keys, I'd lay on a beach in a lounge chair and watch the stars for hours. This is almost as cool. Yeah, I have to say, almost as cool is a way to put it. That's true. Because it's not like you're laying on a beach, but at least you got the lawn chair. Now, what you could do, though, you might have a nice recliner. What you might want to do is put it up on your big screen if you got one. A lot of people like to put our streams up on the big screen. I mean, look. Here, and here's what I like to do. Watch this. Okay, so we have this is underway right now. I'll color correct just a little here, and when I color correct, you see subtle changes occur, and the reds will look a little redder. You can see more reds showing up here and here. Okay, and you see dark nebula all down here. This dark thing sticking up. And as time moves on, this is going to get way better. So what I'll do is I will undock this right there and move it down. Okay, and then I will maximize this and pull this over. Okay, so now we can just full screen. And now for those of you that want to put it up on your big TV, there you go. You got that right there,
Wow.
All courtesy of SkyTour Live. Act now, and we'll send you free Slim Whitman's greatest hits. No, I'm just kidding. I don't know.
Okay.
That's really pretty. So, a lot to unpack in this image. This is called the Christmas tree cluster. This is a cluster of young stars. This is a stellar nursery that it's within. Okay? We have hydrogen gas that glows red like we've talked about. All right. We also have blue nebula. This is not green. This is blue. That's different from the other nebula we saw. Okay. This is dust that is scattering starlight. And it's called a reflection nebula because what it does is it reflects the blue light coming from the stars in all directions. It's actually scattering. The actual process is called Rayleigh scattering, but who cares, right? The thing that's important is if there's a lot of dust, like in this region, there's a lot of dust in there. And this dust, actually, you know what? Let me just go do it. This is a lot of dust in here, okay? And the dust in here is very, very small grains, and these very small grains can scatter the shorter wavelength of light, which is the blue end of the spectrum, blue light from stars. And so you get this blue glow. This is dust scattering the light from the stars. It's mixed with hydrogen being ionized by these same stars, giving it a reddish glow. But you'll notice that this stuff isn't the same red as this down here. Why is that? Well, it's because that's a lot of dust up in here, and that dust is scattering blue light, but there's also hydrogen in there. There's also that was a little accident. He had a minor earthquake. The dust.
Really?
No, I knocked over my camera.
Okay. I was like, whoa.
Yeah. So this dust, there's dust in here scattering starlight. So we have a blue color that's being emanated from there, and we also have a red color of light being emanated from there because there's hydrogen gas in here that's giving off the red light we talked about. That's called hydrogen alpha. All right. Well, in light, when you add colors together, you get different things than you get with paint. So we get this kind of magenta hue here because that's the combination of red light and blue light, all right, with light. And then over here we have this beautiful reflection nebula where there's mostly dust in here. So we actually see mostly dust in here, and therefore it's a more of a solid blue, pure color. Then we have mostly hydrogen in here, okay, mixed with some dust, but not a whole lot. And so we see more red in here than we see the dust. Down here, this is called the Cone Nebula. This is a really spectacular region. And let me see if I can zoom in on that now. We have a ways to go here with the exposures.
This looks like it's travel. Something's traveling through it. That's out like an arrow. So beautiful.
So what this object there is, this is the Cone Nebula. Now this object here, this is why I wanted to focus, because there's two tiny stars here that I want you to see. Okay, this is dark dust, and it's up here in the front, and the nebula is behind it. See back here. All right, so it's glowing from back here, and this dust up front is blocking it. That's why you see this dark shape. It's silhouetted by this glow all around it. Okay, it's a tongue of dark material that comes from all over here. This is part of a massive molecular cloud. All right, and the molecular clouds we see in the universe are plentiful, like you can't believe. So looking here, we see this object. That's the cone. We see that there is this beautiful little cap on it. It looks like a cap. That's hydrogen gas emission. And the stars in the cluster here, these stars are most likely illuminating and causing this hydrogen to glow. So that's a little bit of the morphology of this region. And if we back out a little more now and go back to the top, we might be in a position to see some more detail up top. And we are. You can see more red here and over there, kind of behind me over there.
See all that?
Right? And there's more in here. And you see this magenta nebula up here, but you'll notice now that this magenta nebula is taking on a different look. It's actually looks like clouds. It looks like it has structure now. See that?
Right.
And
oh, look at that. You see that?
This is called the Foxfur Nebula, and it's actually a result of that hydrogen and blue reflection nebula combining the lights of those the light of red and blue to make sort of a magenta. But you'll notice there's some brown in there too. Some of the dust in here is simply truly reflecting the starlight, and instead of scattering, you see how it mixes in. It has to do with density. It has to do with where this stuff is. Like this piece right there, that piece right there, that's sitting up in the front. Okay, so if I go over there, okay, that, like this guy right here, this stuff right there, all right, that stuff right here, that's up here. That's in front of the nebula, and the other stuff is behind it. So we can see that because of the nature of how it's laid out here. So there's a you can tell what's on top of what by looking at these images many times. So the Foxfur is in front of this blue nebula.
He's absolutely right. You see that here?
Mm-hmm.
Donald says, when you said Foxfur, I thought I saw three-eyed fox head, and I think it's like this area here, right next to this brightest star, to the right of the brightest star.
So
there's like this facial feature.
You hear? You mean?
Right there. Yes, and down just a little bit.
Okay.
It's like an open mouth type deal. You see that?
Yeah.
Yeah.
That's awesome.
But it's a Foxfur Nebula because it has this cloudiness to it. It looks like fox's fur. These are colloquial names. These are not actual names. If we actually go back here and look, in our planetarium view, we'll see that it's the Foxfur Nebula, the Cone Nebula, and the Christmas Tree Cluster, right?
Okay.
Yeah. And
we should just rename them all.
I know.
Right?
Right.
We're doing our own thing here at SkyTour
Yeah, I know.
Live.
We already got Tiffany's. We already got Tiffany's candles. Okay.
Right. There it is.
Now, what are we gonna have? Are we gonna have you?
Right. Name. The best name for a certain nebula or cluster of stars wins a psionics. There we go. Bam.
Well, be careful because people are going to think that you're saying that you're offering that contest now.
Right?
He's not, folks. He's not. He's musing out loud. He probably should have been on.
I know.
I kid.
Yes. Okay.
This guy.
All right.
Amazing. Absolutely stunning.
So there you go. The fox fur is showing detail, and we've actually right now we've actually stacked 23 images. Now here's a rule of thumb. Okay, let me just bring back our stack for a minute here and dock it up so I can do a couple of housekeeping things. If I run this line over, I'm intercepting more of the mid-range data in here. You know, all the colors. All right.
Mm-hmm.
And so by bringing this in a little bit more, okay, you'll notice that it's going to get a little brighter, and then we can move this guy in. Okay, there we are.
Okay.
Now you can start to see some of the detail in there. And it is very much so highly dependent on how many photos you've taken. But now look at the detail that's showing up in here.
Wow.
See, there's a lot going on in there now, right? And if we color correct that,
Yeah, you see that?
we color correct this, and now by color correcting, you'll see there's a lot more reds all throughout this image, and now you have this black region. These are dark dust clouds. Remember that supernova we looked at, the Crab Nebula supernova?
Right.
When a supernova occurs, it's usually a gigantic supergiant, red supergiant. Well, they're so big, like I said, they could be out to the orbit of Jupiter in size or bigger, okay?
Right.
When they're that big, what you end up getting is that these stars, get out of there, okay? when you get these stars that big, they actually make molecules in their outer atmosphere, and those molecules are extremely tenuous, and the far reaches of a star's atmosphere, they can exist. Many times they're carbon molecules, silicon molecules, and then once they are liberated from the star, they're pushed way out from the star. And even though you get ionization, like we're seeing ionization here, okay, for a different reason, not a supernova,
Right.
even though we see ionization, okay, this dark dust is sort of like a protective layer. And when you have stuff inside that dark dust, you can get ices forming on the surface of those dust grains. And so you get these really icy particles of a material. And all that stuff, and all those ices that make up these dark nebulae, the particles with ice in them, they are literal building blocks of planets and stars, pent up in these little dust grains. And when another star forms in a nearby cluster and heats those grains, it drives off those elements and those compounds, and we end up with a beautiful primordial soup of planet and star building material. And it really means that for life, to build planets, you have to have lots of this dark dust. So I quite literally mean it when I say life began in the dark, right?
Yeah.
It began in the darkness. In this dark, because once you're in this dark, when this dark nebula gets denser, it protects what's inside from the sharp, stark, sterilizing ultraviolet light of these new stars that are in these clusters. So it's all a very protective sheath. And if you folks out there watching the Eagle cam, where the eagle is sitting on her eggs at Big Bear, if you look it up, Big Bear Eagle, okay, you'll find that she's protecting her eggs. Well, in the same way, the dark nebula protects the planetary building process inside of a dark nebula.
That is such a good analogy.
It is, because the mother eagle protects those eggs at all costs. The dark nebula is going to protect from this harsh ultraviolet radiation making its way in, and so it protects the young potential burgeoning star system in there that may have planets of its own. Pretty cool.
Isabella says, life is supposed to be everywhere in space. How can we not find it yet? That's the goal of our global Skywatch network.
That's right.
That is the goal.
Well, I can...
We will find it. It will be one of you guys that finds it.
I can answer a little bit of that question. Okay, she's referring to the Fermi paradox.
Yeah.
Okay, and by the way, that paradox was wrongly attributed to Enrico Fermi. It wasn't.
Yeah.
He was having lunch with guys like, and he worked with Oppenheimer and Teller, okay, and Niels Bohr, and they were having lunch, and it's actually unclear whether Enrico Fermi said it or someone else said it, but it was attributed to Fermi. But the bottom line is, he basically said, they basically said, well, if life is out there, where are they? Shouldn't we have found us by now? And the answer is that yes, they could have. However, what do you do when you want to go explore a herd of elk? Okay, do you just charge right into the middle of the herd and say, hey, let's grab one and put a radio collar around its neck?
Yeah.
No, what will they do? One of two things. They're going to run away, or they're going to attack you out of fear and stomp you and kill you.
Right.
An elk is nowhere near as intelligent as you are. However, it can kill you if cornered. So, obviously, we're not nearly as intelligent as species that may, this is beautiful, that may herald from these regions, okay?
Right.
But we can kill them. They're afraid of the primitiveness of our species, and for good reason, because we are primitive, right? So,
unfortunately,
creatures that are out in space, when they come here, they're going to invest a lot before they get here. They're going to invest a tremendous amount of technology to remain hidden. And
that makes sense.
And I think that the way they do it is based on how they got here in the first place. It automatically provides them with the ability to hide on command. And the reason is that it's that fifth dimensional travel I lecture about around the country. If you are able to shift out of the X, Y, and Z moving through time, our 4 dimensions, and shift into this fifth dimension over here, the farther into that fifth dimension you go, and that actually has a name, it's called the bulk, B-U-L-K.
Bulk.
Yeah.
Okay.
If you can get into the bulk, by generating these particles which pull you into the bulk, if you generate enough of those particles, you go far enough in, right? So that then when you look back where you want to go, you can punch back in light years away from where you were. But if you're only going a little bit, all right, and you oscillate back and forth, all right, this is how you see, for instance, a UFO going through our sky and going all over the place in the sky.
Okay.
This is how you can go hundreds of knots underwater and not really show a trace, because you're not here and you're not there. You're neither here nor there. Okay, you're shifting in and out at high speed, so therefore you're tenuous to both dimensions, both sets of dimensions.
So you wouldn't necessarily need something like a Star Trekian inertia dampener.
No, as a matter of fact, they feel nothing inside. They don't even have propulsion. All they do is shift into the other dimension and then shift back into our dimension. They don't even have propulsion. And if you look at the ships, you notice that many times they were always round. And remember Kenneth Arnold, flying saucers, skipping right? Okay.
Right.
Well, they're round, I believe, because they're particle accelerators. And we make particle accelerators that are big round loops many miles around. CERN is 20 plus miles, right? Okay.
Right.
And we accelerate particles near the speed of light, and we keep them in a gentle curve with very powerful magnetic fields. The consequence of those powerful magnetic fields is a very deadly radiation called synchrotron radiation. And synchrotron radiation would have to be dealt with by any advanced species that wants to create particles that can take them out of our 4 dimensions. Okay? So that's why an alien ship that's a UFO that's round has probably got a particle accelerator in that outer ring, okay? And the inner ring in the center, that's where the occupants are. And they can just go back and forth very quickly. And by going back and forth very quickly from that 5th dimension and back to our 4 dimensions, it's all computer controlled. They don't even care. They can sleep. They just set the computer on autopilot and tell it just go bzzz and go back and forth the whole time they're here. No energy,
Okay.
no sweat, because it's a particle accelerator doing all the work. They just need to have the basic atomic elements, and they're probably reclaiming some of them, a little bit of them anyway. But everywhere they go, they can get new fuel here on our planet. It's very simple. So I think that it's really important to think about the possibility that, Star Trek's warp drive, it might be a fantastical thing,
Right.
but there are really no science fiction shows that illustrate the Kaluza-Klein hypothesis. Yeah, but I'll tell you this. If you look at CERN overseas, they built the Atlas project, the Atlas Accelerator. The Atlas Accelerator was built in part for the express purpose of studying Kaluza-Klein gravitons and finding that if their existence is real. The Kaluza-Klein graviton is the linchpin, because that's what you surround your ship with to pull yourself into that fifth dimension, because that's kind of where they live. So CERN is building, or CERN is looking at, or has built the Atlas Accelerator, and they're investigating Kaluza-Klein gravitons. Meanwhile, in fact, if you look up CERN and Kaluza-Klein gravitons, you'll see papers up there that illustrate exactly what they're doing. On the other hand, go across the ocean to San Francisco and go to Lawrence Livermore Labs. Okay, this laboratory, of course, has been studying fusion, trying to get fusion to work, right? Well, one of the things that they did, which was actually very successful a couple years ago, was to make a sustained nuclear reaction, a fusion reaction. Now, sustained reactions are important. A momentary, crunch of atoms, that's good, okay? You got past that. But it's a very, very hot reaction, so you have to contain it somehow. So they figured out the containment methodology, and they made a sustained fusion reaction for a period of time. Excellent. That's the next step. They put more energy in than they got out. They didn't break even. They didn't get more energy. Yeehaw, the fusion was working. No. But they did the sustained fusion reaction. That was the key. So it means that fusion reactors are in the future. Okay? And overseas at CERN, the Atlas project is showing that Kaluza-Klein gravitons might be in the future. And if that's true, you take the Kaluza-Klein graviton, you take the particle accelerator fusion reactor, marry them together, and we got interstellar travel.
Right.
So it's a very possible. It's very possible, yeah.
Hopefully in the near future.
Yeah, Mr. Django says, "Wow, look at the Christmas tree! How beautiful it became." Yeah, it's true. It is. Let me just drop this a little bit down here.
They did come in great. Oh, sorry. Here you go.
There it is.
Right.
Isn't that pretty? Now you see, now that we've got more exposures, you'll notice that there's so much more stuff around here. See that?
Right.
Yep.
So many more structures.
Oh, this is really pretty. So let me... Yeah, so here's what I'm going to do. I'm going to label this Christmas tree.
Izabela, simple piece of cake. we should have that technology in the next decade. Oh God, I wish. That would be great.
Yeah.
Question for you, Mark. And this is sort of a. So the element, or is an isotope element, helium-3.
Yes.
Bombards our moon. I read a paper suggesting that it could be mined for
fusion,
a nuclear reactor.
Fusion,
fusion,
yeah.
Yes.
Yeah, helium-3 is one of the isotopes that is in the line of fusion fuels. Okay, when you look at how fusion works in the sun, two hydrogen atoms come together, all right, and they form an isotope. Okay, they make more hydrogen atoms at the end, incidentally. But when they come together, you end up getting a neutron that ends up getting absorbed into the hydrogen atom, and that becomes an element, a compound, an isotope called deuterium. Okay, add another neutron, you get tritium. Tritium's another fusion fuel. Okay, helium-3 is the result of fusion from hydrogen atoms, and you get helium-3, helium-4. But the helium-3 in particular is something that is available and able to be mined from the moon, and so we don't have to make helium-3. It's there, right? It's there as a natural isotope in the regolith, so we'd be able to use that.
And it doesn't show up on it doesn't show up here in abundance because we were protected from the bombardment of that isotope, right?
Yeah, we don't have a lot of helium-3 in our regolith, our soils at all. No.
Right.
And it shows up, and remember, it's bonded to other things, so it has to be extracted and refined.
Right.
Wow, look at this.
That would be amazing if we can do that in our future, or get that,
I agree.
in the near future.
I agree. Wow, look at this. Something else.
That is beautiful.
Oh, yeah.
This is just, I love this here. I'm in awe of this here. The cone.
Yeah, the cone is very stunning.
It is.
And I'm going to do this. I did this, if you guys saw it on my Facebook, SkyTour, and a bunch of other groups, I did an analysis of the Rosette Nebula, and I showed features within the Rosette Nebula. I measured their lengths, and I calculated how big they are in real life, and then used the diameter of the solar system as a reference. And if you zoom in to this as far as it can go, you can basically get to 1 pixel, right? And I don't know if I can do that very easily. We'll find out. All right. It won't go very far in beyond this, but there's the
that is cool.
There's the pixels right there. See the pixels?
All right.
Okay. Now, based on the distance of this nebula, the size of this pixel here, okay, is going to be a certain amount. Now, the measurement in the sky is 0.98 arc seconds per pixel. That's what the size of this is right there, right? 0.98 arc seconds. So you add up these pixels, and you can figure out how big the image is in arc seconds. Okay. Now, an arc seconds is a measurement that we use a lot. However, knowing the distance of the nebula and that there's 0.98 arc seconds per pixel, you can actually calculate the size of features. And I did that with the Rosette Nebula. It's on, like I said, my Facebook page, and check it out. And you find that things like this are like this obscene number of light years in size.
Right. Obscene is right.
And that's what's interesting.
Wow.
Yeah. Like in the Rosette Nebula, which is 5,200 light years away, there's these little tiny Bach globules, these little tiny globs, dark globs, very, very, very tiny. You can't see them unless you zoom way, way in. All right?
Okay.
And it turns out that the smallest one is like 141 solar system diameters in size. Okay.
Our solar system,
141 solar system diameters in size. At that distance.
You still can't even.
Yeah.
Right. I mean, some people can't even fathom like the distance between our sun and Pluto or Neptune.
I know. Oh, Izabela just put up the post right there. Thank you, Izabela.
Oh, good deal. Thank you.
She is. You know what? She is always on top of things. She's always on top. She's unbelievable.
Oh. Michael actually asked a question. Do we know what percentage of the stars in this image are sunlight with Earth-sized planets hypothetically?
It depends if there's been a study, Mike. To be honest, so I can't say for sure. I can tell you this though: inside these nebulae like this, where the open nebula is here, stars that are in here, you notice how many stars you see here, okay, and around. But then in some of these areas you don't. That's because they're blocking the stars that are behind them. That's that forward stuff is in front. And this dark nebula right here, it's not that this is a void with no stars. This is dark dust that is blocking the stars behind it. Okay? So we can't tell unless there's been a planetary study by James Webb. We haven't peered into the darkness into the infrared world of the Christmas tree region to know that yet. But that's a really good question. Okay, I'm going to save this one more time. And then I'm going to move just a tad south for just a moment, just to show you what I'm going to do here. Okay.
Obscene light years, Renee. You are absolutely correct about that.
Yep.
It's just
It's an
mind-boggling.
obscene number of light years in size.
Yeah.
Yep. Okay, let's bring this up. And now
Michael, sorry about that. You meant sun-like.
yeah, I figured that's what you meant. That's what I was answering.
Yeah.
Let me bring back my telescope here. There we are. And now what I'll do is I'm going to move us south. You'll see why in just a minute. There we go.
This is really,
there.
really fun stuff. Absolutely fun stuff.
That little fuzzball right there.
Yeah.
Now,
Check that out.
this is something that is an impressive little nebula. And you might say, it's tiny. What the heck is that stupid thing?
Please.
This is an object. Actually, when I was getting my degree in astronomy, this is one of the very first objects that I started to explore. And I took lots of pictures of this. And I actually took them on glass plates. Okay, because that was the most stable emulsion for then doing measurements, which is kind of cool. All right, so if we zoom in on this, you'll see get a little wind there. There we go.
Wow.
Yeah, so right now it doesn't look like much. Okay. All right, but there we go. We got it back.
Kind of resembles a comet, doesn't it? With it like a small
kind of
tail?
does.
Like
Kind of
just-
does. But what I'm gonna do now is
If it angled a certain way?
Yeah.
I'm gonna do a longer exposure of this guy. I'm gonna take us to maybe 25 seconds on this one, because I'd like you to see what it's got to offer. All right.
While it's coming in, I'm going to use the little boy's room. Be right back.
Okay. Well, what does Tiffany use?
I know.
Oh, it's interchangeable. There you go.
Oh my gosh.
All right, be right back.
I'll be right here.
You can.
Okay, let me get this running. There we go. Waiting. Okay. That'll be up on the server. You can grab that if Izabela put it up. There is the first image. This is a beautiful little nebula. And this is only one. This is sort of the first one. Remember I talked about that stack? So you take the next image, align the stars, stack it on there, stack it on. All this noise that you see outside, don't worry, it's coming back. All this noise that you see on the outside, and that was a rejected frame. Okay, gotcha. Yeah, that's why. See? All right, I'm going to clear it. But all this noise on the outside here that is in between the stars, that's all going to be softened over time. So I'm clearing this to start this again. All right. There we go. So there's Hubble's Variable Nebula. Now it'll, as it comes in, it'll start to resolve into something much more interesting. I'm going to drop this down into the 8s. Let's see if that helps. Yeah, okay, now the second one comes in, and look, see that? How much noise went away? And that's what happens here. So this little fan-shaped nebula doesn't look like much, but what it represents is very interesting. When you look at this nebula here, you think there's got to be something illuminating it. It's not glowing red, is it? It's actually kind of glowing kind of whitish blue. That's because it's a partial reflection nebula and reflected light nebula of the star that's causing it. So where is the star that's causing it? You might think that it's this little star here. It's not. What's happening is this sharp wall here, right on this edge, okay? This sharp wall is actually a dark nebula, okay? And when you look at the sky, you see clouds that look sharp because, like cumulus clouds, they look sharp because you're far away. Well, we're very sharp, and we're very far away from this wall, so it looks sharp. But if we ended up getting closer to this dark wall, we would see that it's actually much more subtle and spread out. Okay, so what's going on here is inside here, this darkness, this is all dust out here, all dust out here. There is a star in here, and that star is surrounded by dust, we think. Okay, and as that dust orbits the star, sometimes it gets in the way of the starlight that's reflecting on this nebula. And that starlight that reflects on this nebula, all right, gives rise to changes in brightness of this nebula. Therefore, this is called Hubble's Variable Nebula, found by Edwin P. Hubble.
Awesome.
Yeah. And so, over a period of just a few days, you can see a change in its brightness as the dark clouds circling the star end up getting in the way of the light, and you'll see it change. It's like a shadow puppet on the wall, and the wall happens to be this dust. It's really interesting watching it happen. You know, that's kind of cool.
That is very cool.
Let me drop this down and soften this up a bit.
Michael has a question when you're available.
Yeah. Oh, Michael Hedrick, how you doing, man? Would noise ever come from very distant light, from very distant stars? I always wondered when looking at space images, or would that be a different frequency? Noise? Would noise ever come from very distant light, from very distant stars? Noise. What's he talking about? Hey, Gladys.
Clarify.
Hey, Gladys. Gladys is here. MPG, how you doing? Michael, can you rephrase the question? I do not know how to answer that question.
Camera noise.
Is that what he said? Oh, camera noise.
Yeah. Yeah.
Oh, I see what he's saying. Okay. No, the camera noise is actually built into the camera. I know that sounds kind of simple, but it is. It's the noise of the camera. If you look at our temperature down here, we're at minus 23.5 Celsius. Okay. And our temperature in the building is 13.8 Celsius. Okay. So it's pretty warm out there in the building, relatively speaking. And the camera sensor is minus 23 Celsius. So we're actually cooling that camera sensor down, because the cooler the camera sensor is, the less noise we'll see. As a matter of fact, we've got 9 shots here. Watch this. I'm going to take this all the way over to the right. And it's going to soften the noise even more and show you more detail. Nice. See that?
Beautiful.
Yep. And now we can zoom in on that a little bit more and start to see some of the details in here.
Oh, yeah. Oh, yeah.
So that's what's going on there. So this subtle differences and the subtle colors. The brown is the dust. The white is the reflection mixed with reflection nebula, the scattering of the starlight by the dust. And the object, this star is not doing it. This star is just an interloper in the field. It's actually inside this dust cloud. You can't see the star causing this.
Okay.
So this is all, you can almost see the dust hollow in here. It's sort of in here somewhere.
Oh, I see.
I think. I mean, I don't know, actually. James Dugan is joining us from Australia.
That is super.
Hi, James. How's it going down under? Good to have you with us. No, Renee Cruz, noises and sound. No, noise as in this static-looking stuff around the image. This is generated by the sensor. When the sensor on the camera is very sensitive, and if you're pushing it with high sensitivity, like I am, this here, you can barely read that. It says 250. The sensor setting is 250. It's very, very high. It goes as high as 300. Okay? And the sensor setting for almost no noise is like approximately 100 or even 50. So this, I'm pushing it on purpose. Yeah, MPG has a question too. How do you decide how cool? Oh yeah, that's a very good question. How do you decide how cool to keep the camera? So what you do actually, MPG, is you look at the temperature in the building. It's 13.8, and you want to try and drive the temperature like 30 degrees below the temperature in around it, and that's the relative coolness that will actually minimize the noise. So we're at minus 23.5 right now. Obviously, you add 10 to that, and you're getting 13.5. Add 10 again, and you get, minus 3, and then you just keep going like that. So we're a little more than 30 degrees below ambient right now.
That is very beautiful.
Yeah, it's neat, and seeing these details around the outside are very nice, and usually those get washed out when you have this thing up here. Okay, as you see, it kind of gets washed out.
Okay.
And let me just color correct here. There. So I color corrected. Now you can start to see some of the natural dust colors showing up. And if we bring this down here, you can start to see, see the colors. This will pop in, and it's like, there it goes.
Gladys.
What? Oh, Gladys? What Gladys say?
Hi, Gladys.
Oh, who are those people below me? Oh, I'm sorry, Gladys. You know what? It doesn't appear in the title. You're actually right, and I probably should have stuck you guys in the title. I'll go back and do that.
That's fine. Yeah, we're not worried about
Okay. Okay. All right. Okay. This guy here is Calabos in the chat, and this woman here is Tiffany. All right. This is Calabos and Tiffany Echo. These are the people we see in our chat, and they are also SkyTour livestream volunteers, and they're also the people.
Telescope people.
Oh, the telescope people. Yeah, there you go. That's right.
Hello, Gladys.
That's
Pleasure to make your acquaintance.
That's funny. Yeah, the telescope people.
Face the camera.
That's right. That's right. Telescope people is right. And me, I'm just alien people.
As opposed to the TV people. They're here.
Yeah. So you see, this is just beautiful. You know, I really like this. It's hard to see it through these glasses, though, I gotta tell you. You know, and you guys don't see me with the glasses unless you look at the actual feed.
Yeah.
So,
oh no, you got
no.
so you finally saw them. Okay. Yeah, that's okay. Well, look, you know,
Wow.
folks, take a little vote. If you'd like to see Tiffany and Calabos on the stream in the future, let me know, and we'll bring them on. I'll grudgingly bring them on because they're kind of okay.
I know.
Hello, Cindy Murphy. Cindy Murphy is actually one of the people in our chat who has been with us a long time, and Cindy has been getting some of our SkyTour shop merchandise. Okay, SkyTour shop is where you can go to get these images on, like I said, sneakers and bedspreads, mouse pads, bathing suits, and yes, even underwear. There's boxer shorts with nebulae on it. Yeah, Okay.
Awesome.
Yeah. So I
Bathing suit
designed.
for contact.
There you go. Bathing suit. Yeah, they got bathing suits with this stuff on them too.
But if we get her a bathing suit, we're not going to be volunteering for your night thing because we'll be too busy in the jacuzzi with stars.
I think
Oh,
you
my
know what? That's okay with me. Okay. Michael Hedrick. See, Michael Hedrick says yes. He's voting multiple times, which is illegal.
Oh, yeah, that's illegal, man. You can't be doing that.
Yeah.
Where's my votes?
Look what Gladys says. Okay.
I'm doing no.
Gladys is.
Yeah,
She's got a sense of
Thank you.
humor. Gladys has a sense of humor. See what she wrote?
Typing and speaking so
She
talented.
writes, "Breathe once if Mark's keeping you
Oh.
captive."
Yeah,
Yeah.
What?
we're being captured. Help! Help! Help!
Yeah. Mr. Django is
Oh,
still with us. Mr. Django usually at this time, if we stream during a weekday, he has to head out to work because he's in
Yeah.
Belgium. So this is pretty cool, isn't it?
Thank you for having us here. Thank you for having us. Thank you for joining us.
Oh yeah.
Amazing. Love this stuff.
Yeah.
Absolutely.
Mr. Django.
And thank
Mr.
you.
Django is
We kinda
really
wanted to-
cool too.
We kind of wanted to put a face for you guys to see as Gladys put the telescope people. So yeah, hopefully we'll be doing this a lot more during the week. Unfortunately, we might be able to come through, but because I wake up at 3 a.m, like literally, what time is it now? It's 9:15 Pacific Standard Time. So I'd probably be like, hey, gotta go, guys. Gotta wake up in 6 hours.
That's right.
So, yeah. So I gotta keep going to work, so I can get those telescopes for you guys, binoculars, whatnot.
Yeah.
Yep.
Yeah. Hey, Puck
Those dollars.
Puck Alpha's with us. Nice to see you.
Yeah.
And Steve Tuttle, nice to see you, man. He asks, hi, are the red stars due to their redshift or the type of star? Actually, the type of star in this particular case, Stephen. The most plentiful star, I'm going to back out because we're actually zoomed in quite far here to see this particular little nebula that we're looking at. But, okay, you notice all the red nebula in this region. This is all what's called diffuse nebula. It's excited hydrogen nebula. And the hydrogen gas is glowing red in the light of what's called H alpha. All right. So this particular nebula is in this region where there's lots of dark dust. See this dark blot? This is not a dark blot where there's no stars. It's not a void. It's actually an area where there's a lot of dust. Now what happens is sometimes the stars are within the dust. And when stars are within the dust, then what will happen is you'll see that the stars might look like they're a little dimmer, like this, okay? And like that, and like this right here. These are stars that might be within the dust cloud, but you'll notice that most of them are red. And they're red because of two possibilities, okay? Well, several possibilities, but two main possibilities. Number one, their light has been reddened by the dust between us and the star. Okay, when the sun is on the horizon, it's red because the sunlight is going through more particles and more molecules in our atmosphere, and more of the blue light is scattered out of the sunlight. So the sun is left with just its red part of the spectrum. All right, so that's why our sky in the horizon, the sun looks red. All right, and these red stars, okay, so that could be part of the reason because of the reddening of starlight through dust, okay, just like our sun on the horizon. Similarly, it could also be due to the fact that these are what are called red dwarfs. Now, when you look at the stars in the sky, the hottest bluest stars are the O-type stars, and it goes O, B, A, F, G, K, M. All right.
Okay.
And so the hottest and bluest are O, and the reddest and coolest are the M stars. M is in Mike. Okay. All right.
Go figure.
Yeah. Well, there's,
Too many Michaels in the stream. Michael.
yes, we have
You, Michael.
Michael Galea, we have Michael Hedricks, we have, yeah, that's right, we have Michael U. Okay.
Michael me.
Yeah. And so the red stars then could be these red dwarf stars known as M-class stars. So nothing like when Star Trek says an M-class star, they don't mean this red star. They
Right.
mean, they say M-class planets. Well,
Right.
okay. Science fiction versus reality. So anyway, here,
M
when you
class
look here,
Mike.
okay, these red stars then are possibly red dwarfs. Now, why do I say that? Because red dwarf stars, M-type stars, okay, the OBAFGK M-type, reddest with coolest surface temperatures, are the most plentiful star in the entire universe. There's more of them than any other. And here's a little magic fact for you. Because they're so small, and because they radiate their temperatures at a much lower rate, okay, they radiate their radiation rather at a much lower rate, they last for so long that the very first M stars that were ever in the universe have yet to die. Wow. And the universe is 13.8 billion years old. The first M star that formed is still out there now, first M dwarf, okay, the small M star. So that's why they're the most plentiful. And there's another thing about M stars which are really cool, and that is M-type stars have more planets around them than any other kind of star. That doesn't mean like every M star has 1,000 planets around it. No. It means that almost every M star out there, on average, will have a planet around it. And most stars you see in this image, okay, in general, there's more planets in the universe than there are stars. And that is the cool brain exploder for tonight.
Right? Well, oh man, can you imagine? I have a question for you, actually.
Yes.
So, the red dwarfs. I remember we were speaking about how red dwarfs, if red dwarfs had planets around them, that most likely they would be tidally locked within the Goldilocks zone.
Yes, as a matter of fact, let me unpack that for everybody.
Okay.
When you talk about a red dwarf, they're really literally 1/100th of the output of the sun, maybe a 1/10th of the output. Very, very small, sometimes only slightly larger than the planet Jupiter. When we talk about red dwarfs and their star systems, it makes more sense to talk about Jupiter and its moons than it does to talk about the sun and its planets. That's how big a scale difference we're talking about for these stars. But when you look at a red dwarf, if a planet is going to be in the habitable zone, not too cold, not too hot, the Goldilocks zone, yay, okay, where life could exist, where it's warm enough, where the water could exist on the planet, you're talking about having that planet so close to the star that in nearly every case of M stars with planets, all the planets around the M star are closer to the star than Mercury is to our sun. Every one of the planets in those star systems are within the orbit of Mercury to its star. And if they were at Mercury, they'd be frozen glacial worlds. But somewhere closer, you would end up having a point where you could have a very warm and ideal potential living spot, for, life. Now, these M stars, and this is coming in nicely, so we're going to keep it going. These M stars, also, because the planets are so close to them, the planets go around the star very quickly. So, for us, a year is 365 days. January through December. Okay? On an M star, your year is going to be measured potentially in just hours and maybe just a couple days. There's like the TRAPPIST-1 system is one of my favorite I call it a pet star system, because it has a number of planets, and it's potentially true that 3 of the planets around that red dwarf system are in the habitable zone, where you could potentially have life if the planet has an atmosphere, if the planet has liquid water on the surface. Okay, all interesting. But now consider this. Because the planets are so close to the star, there's another factor that comes into play, and that is that the stars, hey Marianne, Marianne's here, that the star, okay, imposes an interesting gravitational quandary on the planets that go around it. And that is that the star and its planets, an M star, act like the Earth and its moon. The moon has one face facing us at all times. So the same face as the moon goes around, the same face of the moon is facing us. That's because the moon is tidally locked to the Earth. Tidal locking just means that the gravitational forces add up such that the planet is locked with one face facing what it's orbiting. Okay? I could go through a lot of details about how tidal locking works, but never mind that for now. Let's not get lost in this part. So, with all these red dwarf stars, their planets are tidally locked. So think about this. You're a real estate developer, and you're developing Proxima Centauri b. Ah, wow. What does it have to offer? Well, lots of sunlight if you go on the star-facing side. So you have a vacation hotspot where you'll always have the sun. And then it offers phenomenal sunsets the whole year round.
Right.
All day and all night, so to speak.
Imagine that.
You go to the edge where it's tidally locked, you always have sunset. Wow.
Can you
I
imagine
got the most beautiful pictures at Proxima Centauri b. Wow. Okay. And then the astronomers went to the dark side of Proxima Centauri b and said, I saw a year's worth of stars in just a few days, because that's the time it took for the planet to go around its star. So I saw a whole year of stars from Proxima Centauri b. I mean, it's a real estate bonanza if you can get there.
Yeah. Oh, yeah.
Yeah. Permanent tropical sunlight, permanent beautiful sunsets, permanent stars. Now, let's talk about the reality. Let's say it has an atmosphere. The sun side of that atmosphere is going to get heated up pretty hot. Okay?
Yes.
And because it's heated, it's going to expand. And when it expands, that expansion is going to start causing very, very powerful winds. And those winds are going to manifest themselves as full global winds that are going to go around that edge through that beautiful sunsets. And you might end up with several 100-mile-an-hour winds raking through the sun to dark side of the planet. And then you're going to end up with these very, very powerful winds going further into the dark side of the planet, okay? And you will end up having potentially atmospheric mixing. So the temperature on the front side is going to be, say, hot. Let's say, for a record, it's 110 degrees all the time there under the sun. Well, then when you actually end up going to the dark side of the planet, it might be 90. It might be 85 on the dark side, even though it's on the cold side. Because the atmosphere with such winds are globally mixing at all times. So that said, you're going to end up with this very strange thing. If it's always cold on this side of the planet, always hot on this side of the planet, the transition zones are going to be turbulent hellscapes. It's going to be very, very, very turbulent. So it may be that it's not as romantic, not as exciting as I was painting it out to be. And if I bought real estate there, I'd probably go bankrupt. However, there could be life there. There could be life that lives on the dark side. There could be life that lives on the bright side. The transition zones might be too turbulent. Yeah, it's like a permanent Cape of Good Hope all the way around the planet. As you're transitioning, maybe. So that said, it could be pretty bad there.
Would that actually change the distance of the so-called Goldilocks zone then? If you were to pull that planet back a bit further, so it wouldn't be just this oven cooking on the sun side.
Well, remember, it's a matter of comparative temperatures, right? Let's say you set it out a few more, several 100,000 more miles. Okay. All right. The sun side drops by, say, 10 degrees. Let's say. And the backside will drop by a similar amount. But you still have the gradient, the difference between this hot and this cold, right? And that's going to generate these winds no matter how far out you go. See? The only way you won't get those winds is if you're so far away that the planet is practically fully glaciated.
Oh, yeah. Right?
So then you'll have always very, very, very cold temperatures at all times. But that said, I think M-stars provide the best opportunity for there to be some type of life. Now, M stars are also extremely turbulent themselves. They have lots of ultraviolet radiation when they're young, and they're known as flare stars. They give off a lot of flares, and the flare stars could really sterilize any planets. So, but that's a possibility. We don't know this for sure, do we?
Right.
Yeah, because we can't go there yet.
Right.
You know,
or send anything there.
Not yet. Yeah.
Honest. Not in our lifetime anyway.
So while we have been doing this, we've got these beautiful images now of Hubble's Variable Nebula. Look at this. As I back out, look at this gorgeous image. Look at this dark nebula. You can actually see structure in here. Let's see if I can. Let me see if I can draw out some of that structure here.
It's all dark nebula.
It is. Yeah, dark dust. Yeah.
There you go.
Look at that. There's a beautiful little nebula coming down here. Look at that.
Oh,
Yeah.
Beautiful. So
all this. Wow.
So
look at this.
So see this was all dark when we first started this, but now you see this beautiful diffuse hydrogen. You see it mixes up into here and all through here. Okay. Remember, just north of this is the Christmas tree cluster and the Cone Nebula that we were looking at earlier.
Hi.
Right? So this is all dust in here. Again, the dust is in here, and it's mixed with the hydrogen gas as well. So now that we've got this and we've taken this is probably the longest exposure I've taken of Hubble's Variable Nebula. I mean, it's not longer than it's certainly not longer than the one I did when I was getting my degree. I was using a 20-inch refractor. The telescope was 35 to 40 feet long.
Wow.
Weighed several tons, and the entire floor moved up and down to meet the telescope.
Wow.
So it was a giant elevator you were standing on all night, and you couldn't heat the building because you had to have the telescope at the same temperature as the outside air.
Okay.
Because otherwise, the slit in the dome, well, you would end up getting hot air coming out of that, and it'd ruin your views in no time.
Right.
Yep. And Izabela says, this dark nebula is very dark.
Mm-hmm.
And you're right. Let's see where the processing wants to take it. It'll be a little bit to the left of that. Wow, look at that. So that's more subtle. And I'm bringing it this way, which is going to cause it to look darker.
Mm.
Look at that. So that's just beautiful. Look at,
especially this structure here.
yeah, and look at that now. You can start to see the structure here. Now you see, here's something new. Now you see this red nebula, this red diffuse nebula, punctuated by this black dark nebula, and it goes all the way up this whole piece right there, and then comes across out here.
All of it.
All
I
of
mean,
it's just
really,
beautiful.
just it's so colorful.
So colorful, yeah.
Yeah, we actually have this. I think Cindy in the chat actually has this entire region on a fleece blanket.
What?
Yeah, I did not. Well,
Nice.
this plus the entire nebula above, the Christmas tree cluster and so forth.
Nice.
Yeah, Cindy, if you're still with us, tell folks about that fleece. She'll probably say I'm under it now. Last time I mentioned that, she said I'm using it now.
And Gladys asked, what alphabet of star is our sun?
G.
There you
it
go.
goes.
Michael got it right. It's the Michaels for the
That's
win.
right.
Thank you,
yeah,
Michael.
it's the OBAFGKM. Now I'm going to tell you the little metaphor that I learned.
Yeah, I don't.
The little metaphor I learned when I learned about these stellar types, and it was kind of weird hearing a professor tell me this, but it is something that persisted from the very first time we learned about Ejnar Hertzsprung and Henry Norris Russell and the classification of stars that they made called the Hertzsprung-Russell diagram. And that is to remember those letters, O, B, A, F, G, K, M. You just remember the phrase, "Oh, be a fine girl, kiss me now."
Oh.
Yeah, very sexist.
That's awesome.
Okay.
Yeah.
But see, the women can say if they wanted to, "Oh, be a fine guy," So I mean, yeah,
Michael,
it's still a G.
We don't want to kiss Mark.
I agree, Michael, and I'm pleased that you feel that way. No, we're good. And and by the way, it used to be there were R, N as in November, and S types after the M. So it was OBA, fine girl, kiss me right now, smack.
What?
That's what it used to be. And I used to.
On that. Good night,
Yeah,
ladies
right.
and gentlemen. Have a-
And I used to joke about it. I used to joke about it. Say, "Oh, be a fine girl, kiss me right now, smack, ow!" You know, like smack me. So, but anyway,
Right on.
so the bottom line was that that's how you remember the letters. O is the hottest and bluest, you know, and M is the coolest and the reddest, you know. And that, like I said, it's just a metaphor that was drilled into our heads, you know.
Izabela. Oh, kids.
Oh, kids. Yeah, that's you, Michael. Just talking about you. You.
Grown up
Yeah,
kids.
cut it out, Michael, down there.
I'm never growing old. I got Peter Pan syndrome. Would you like a binocular?
Hey, tell me about it. I am there.
Right.
Let me change this to Hubble's Variable Nebula. There we are.
We Michaels are definitely childish.
Mm.
Forever children.
Okay. All right, I'm going to save this now.
All right.
And that's going to
That's
be
beautiful.
at...
There's just so many amazing colors in that.
Yeah, I never, like I said, I never went this long with this before. This is a 28-minute, 45-second exposure.
Wow. Let me ask you this. I do have a question.
Yeah.
What is the structure here? Below, I would say on the left, about, I'd say halfway up the halfway point. So like these yellow objects here. Keep going up with your cursor. Keep going up, up. Getting close. There you go, right there. What is that?
Oh, those are several stars. And if we zoom in on them, let's see what we can see. Okay.
I mean, it looks like a couple stars super close together, right?
Yeah, these are all stars.
Wow.
Now, the thing is, these stars are also potentially partially in this nebula, which makes them look a little orange, or they are red supergiants or red dwarfs. Okay, stars like these guys, these little tiny red ones that you barely see, these are most likely red dwarfs, because at the distance of this whole nebular complex, red dwarfs might look about that bright. It's kind of what we might expect for red dwarfs. If they were supergiants, they would be massively more bright because their diameters would be massive. And so, like, these could be red supergiants out here, of some kind.
Yeah.
These tiny, tiny little baby red ones are probably red dwarfs, M-type stars, you know.
And could it also be distance as well? It couldn't be distance from what we're seeing.
Well, see,
as far as star size.
well, that's what I'm saying. Okay, if we because the size is based on how much light hits the sensor, and it makes the star image bloat. Okay.
Okay.
However, when you see these little red stars, keep in mind that there's all kinds of dust here. So if these were supergiants, they would be a lot further away and probably obscured by the dark dust here. So that kind of gives us a clue that if you see lots of these little red guys, they're most likely M-type stars. These guys here in the foreground, those might be closer to us, and they might be red supergiants. Now, there is a possibility that they're not red supergiants, but they'd have to be really close for them to be M stars, because M-type stars aren't very luminous. This is a very luminous star. It's very bright. Okay, this is very bright. That's very bright. So they're probably going to be supergiants. Actually, we might be able to test this theory right now. So if we go in here,
Right on.
we go here. Let's go over to this. Let's go over here, and let's actually get our stellar field.
Oh, very cool.
Yeah, we're actually down here right now. All right, let's yeah, I'm gonna do a couple things to get this right. First thing I'm going to do is pull this up. All right, we're almost centered. Excellent. Okay, so what I'm going to do now is come in here.
What?
I'm just making sure we're centered. So I'm going to go right here, and I'm going to do what's called a synchronization. So watch the crosshair. This crosshair now is going to go here. Okay, so I just synchronized the telescope. So now we're almost in the center. So this bright star right here, right?
Okay.
Might be that star right there.
Oh, I see.
Okay.
Oh, right on.
So let me actually come out of here. It may not be because I'm actually zoomed in quite a bit. Let me zoom out and get me back to this region here. Oh yeah, okay. Yeah, we're still there. So that star right there is that star. Okay. And we're looking at the little stars you were talking about. We're right here. Right here. Okay.
Yeah.
So what I'm going to do now is I'm going to go in here to our planetarium. And we may not even have those stars in here, but we should.
Right.
Yeah, we got them in here. Okay, there's Hubble's Variable Nebula. And let's back out a little bit and hunt down our bright star again, which is right there. And there we are. So there's one. So let's focus on that guy.
Okay.
Okay. This one, it does not give the spectral type of this star. So we don't... now, there are some stars that are not classified, but nearly all stars are. So that's just a fault of this thing. They're not doing it. If we look at this star, okay, they usually have designations. We have either a Hipparchus number, a Tycho number, and then we could look it up. And so we don't have that for this particular star.
Okay.
So we can't tell that at this point, which is unfortunate. But see, this is where we are.
It's not,
Look, this is where we are compared to the Christmas tree nebula in the cone. See that? We're literally one field down below. And so it's possible that we can actually stitch the one above with this one and make a giant, kind of offset one. And Izabela's thinking, "Ooh, stitching! I love that." We do a lot of mosaics here, and because it's just beautiful. But to do an exposure of this length really showcases what's going on in the universe. Look at all these stars, man.
Right.
Right. The detail is just stupendous. Okay. I think I'm going to stop now with this. Okay, because it really is.
Keep going.
Well,
it gets clear.
I did 30.
No, I'm kidding.
Well, remember I told you have to double 25 exposures to get half the noise and get it reduced. You have to double your exposures basically. So I'd have to go to 50.
Okay.
Well, I went from 25 to 84. Okay.
Oh, wow.
So I've gotten rid of a lot of the noise and
16 more. 16 more.
yeah. Let me just bring that back up again. Yeah, I saved that right there.
50 to 100.
So that's what it looks like in the stack, right?
Right.
Okay, and this is what it looks like without any of that. Look at all, this is just stars to you. You can't really tell, right? But what I'll do is if I go back and add a little more power to this, and not power, but sensitivity. Now you can see this is kind of what I saw with the 20-inch refractor. All right.
Wow.
But it was a lot bigger. Okay.
Yeah. A lot bigger.
Izabela, the stellarium stars are in color. You just may not be able to see them.
Oh no.
Yeah, so that's okay. All right, so
I'm wondering where you went, Tiff.
Well, I'm still here.
let's see if we can do one object more. I did this the other night. I did a lot of measurements in here, and it might be worth showing you guys what I did. I won't leave it on nearly as long, but let's just try going to that rosette.
Oh yeah, the rosette. The one you was talking about earlier.
Yeah,
This is. I saw a picture of
yeah.
earlier.
Isabella put up a
Stuff.
link to my project I did to show you the actual size of things in the rosette. Okay,
Mhm.
but this is the cluster in the center of the rosette. Okay, it's actually quite a good alignment. So I'm going to head to the east a little bit just to bring this over. I heard a cat.
Yeah,
That's my cat.
that's garbage. That's little garbage. She's our recent rescue.
Is that the name of the cat?
Yeah, because we found her in the
Yeah.
garbage.
Oh, that is funny. Well, I guess it's a better name than Rancid Mushroom.
Right, right.
Rancid Mushroom, get in here. Screw you. I'm not coming back with that name.
Right.
Empty soap carton. Empty soap carton. Where are you? Darn it.
Oh, n-
Coast soapbox. Where are you? Damn it. The
Oh,
darn thing is
no.
missing.
moldy
Gladys
strawberry.
is
go,
awesome.
Moldy pepperoni. Where are you?
Moldy pepperoni. Ooh. Perish the thought.
Yeah. Green bread. Green bread.
Bring her? Can we bring her? Does she want to be famous? Come here. She don't want to be famous? Do you want to be famous?
Does it look like she wants to be famous?
No, because she actually gained a bunch of weight, so I think that she knows that the camera adds a lot of weight.
Oh, that's hilarious.
She gained a lot of healthy
She
weight.
did gain a lot of healthy weight. I mean, she's a part. We believe she's part Mancoon, right?
Yeah.
Oh, yeah.
she's
Maine
huge.
Coon. Yep.
She's. Come here, girl.
Maine Coon would be it.
Are you okay with that? No. Yes. Oh my goodness.
Right now, we're gonna get a cat that just like rips him to shreds on camera live.
Are we good? Yeah, she's amazing.
Right,
She's
hang
huge.
on, I can't show her yet because. All right, good. I'm waiting. All right, you ready? Let me enlarge your view. All right, let me see this. Let me see this creature.
Giant creature.
Oh,
Unfortunately, wearing a black sweater.
yes, that's certainly not a lot of help, but it's okay.
Yeah. Oh my goodness. There we go. How's that?
Oh my.
Guitar shot.
Oh.
Guitar shot.
Okay, I gotta take you out of the way there because we have a beautiful nebula here now.
There we go. Thank you, sir.
That was great. Thank you, man.
She's beautiful. Oh wait, you want to go this way, don't you?
Oh my god. Oh no,
There
don't
you go.
hiss at her.
Did I just hear the cat hiss at you?
She's still acclimating. She's acclimating to the other cats that we have.
Oh, so she wasn't hissing at you.
Her
She
and
still gets a
Bandit-
little scared of them.
Yeah, her and Bandit are actually a lot closer than the others.
Bandit.
But they were like literally nose to nose just a
Yeah.
minute ago. I didn't see Bandit right here.
All right.
So yeah, she gave it a little hiss, but she's fine. She went back to her area.
Wow.
We're bad.
All right. So this is the Rosette Nebula. It's a beautiful, gorgeous nebula, and what we typically look at with this nebula is the fact that it has all
Look at
this
that.
beautiful dark
Oh,
dust in
wow.
here. I talked about the shapes
Aptly
of the
named.
dust, and there's something else I talked about in here. I talked about the pillars that appear in here. That was the crux of it. But I'll also come back up here. We may need to have a few more exposures before I can really go through this with you. Well, maybe not. Look, that dark little guy right there.
Oh wow!
That's
It's an
like this
exclamation.
massive.
yeah, that's a Bach globule. Okay, and this right here.
I'm sorry. Say that again.
A Bach globule, B-O-K. Bach, Bart J. Bach was an astronomer.
Oh,
I had
okay.
classes with him actually, and he discovered Bach
Oh.
globules and became famous for the Bach globule because the Bach globules are precursors to potential star systems that include stars, of course, and planets, because they're self-condensing globs of dust and gas, and as that stuff compresses, the interior is getting warm, and the hotter it gets, more massive it gets, the more you can expect the heat to get to the point where something magical may happen in the center, like fusion of this hot mass in the center, the seething hot mass, and that would become a protostar, and that would lead to a star that's born, and that could lead to planets after that, right? So that's what these little tiny things are. There's a million of them in here, all right, throughout this nebula. See, there's one there's one there. Then you have these gigantic pathways, and all of this stuff is sculpted. All of it is sculpted by these hot stars in the middle. And when you back out just a little bit, you can see something amazing with the Rosette Nebula. And that is that this nebula has what looks like a hole in the center. It's like a donut hole. Well, what is that? This is where these hot young stars have literally carved out a cavity in here and pushed the hot gas and dust away, clearing an open space. And a hot young cluster will clear out the gas and dust around it. The clusters we saw at the beginning, the 37 cluster, the little beehive, the big beehive, those were all in nebulae like this at one time. And those ended up being, barren of gas and dust because over time it pushed it away with its stellar winds. And those stellar winds are responsible for sculpting the features in many ways that we see here. Like these dust blobs are sculpted from this very, very powerful stellar wind from these young stars. These are only a few million years old. Wow. But in that time, this distance, which is about 10 light years, actually, believe it or not. Just about from here to here. Okay. This thing is 5,200 light years from the Earth, this overall thing. Right? Okay. So at that distance, in fact, this is something I can do because I did the scaling for this one. If we zoom in on this and we go all the way down to 1 pixel in here, okay, all right, and you see, all right, if we move up here, it'll come up.
Each one.
See that? Each one of those pixels in this particular image is 5 solar system diameters in size. Each one of those pixels.
That's a no.
That's a long.
5 solar system diameters. So you can see that if you're in the middle of this, you might not even see any of this.
Oh,
because, it's all around you and you're within it, Isn't that cool? And I figured
cool, but it's also kind of sad. I mean, because we can see this beautiful structure from a distance, but if there is life that has evolved into an intelligent life living in this structure, they will never know the beauty of this until they were able to exit this structure and see it from afar. So it's kind of like it's sadly beautiful.
Yeah.
When you think about it.
And so, but the sculpting has taken place because of this young hot cluster, and this cavity was created by this hot young cluster. Down here at the other end of the nebula, you can take a look at this region, and it's very telling what's going on over here. Let's check that out. So as we zoom in, right, you'll notice that we have interesting structures that look like they're pointing right at the stars. Right there, pointing right at the stars. Why are these things pointing at the stars? They're pointing at the stars because the stars are eroding the gas and dust. Like they made the cavity, they're pushing gas and dust down this way, away. Okay? And so at the end here, the end of this particular pillar that we're looking at right there is a little bit more dense. So it's able to withstand the erosion from the powerful stars up here. And thus, on the lee side, in the shadow of that large knot of dust, the shadow is protected as well. And so they're protected from being eroded. And so they make a natural stalk or a pillar. That's happening here too. So you see a way in which these nebulae form these structures, and then when you hear about them, that is just an incredible thing. Okay, let's go back to that thing. I want to show you something else because I did a measurement of this one. Okay, all right, this pillar right here, okay? If we look at that pillar and we say, well, how long is that pillar? Okay, if you measure, and I'll show you the line, if I measure from here to here, okay, that measurement is a certain number of arc seconds, which is an angular measure on the sky, right? There's 60 arc minutes in a degree, and 60 seconds per degree, so it's 3,600 arc seconds per degree. And this measured out to be a certain number of arc seconds in length. Knowing the distance of this nebula, I calculated the actual length of this, and it turns out that this right here, this stalk right here, in this gigantic nebula, is literally longer than the distance from here to Alpha Centauri. This is 4.8 light years in length. And by the way, that's the shortest length it can be. That's if it's exactly flat to us. If it's coming out toward us, it's going to be bigger. If it's going in away from us, it's going to be bigger. So the shortest length is 4.8 light years, and it's very likely larger than that. Wow. Yeah. In fact, I think that's probably among the coolest type of things you can do with nebulae, is figure out all these details.
Right.
If you know their distance, and we usually do, then that is what you can do with it. Now, here's another interesting thing. You notice?
Look at that.
You notice?
As he pulls out.
Oh, yeah. Notice when you pull out of here. And let me do another color correction, because...
It's like a blip of the entire structure itself.
Yeah.
A blip.
Yeah, it is. Okay? So you got this massive structure. Now, check this out. This stuff looks like it's a different color from this stuff. Okay? Now, there's a lot of things going on in here. First of all, this gas that's in here, okay, probably was liberated from a supernova. However, it's also possible that this gas was, here from the very beginning of time as well. One or the other, most likely liberated by a star, and there's going to be some hydrogen that's primordial. Okay? But you'll notice this different color. Now, this different color, especially right there, okay, this different color could very well be, and is, as a matter of fact, because we have different elements that are glowing here. This is hydrogen. We know that. And there's actually dust here. This is dust mixed in with the hydrogen, all right? And it's just making these areas look a little denser, okay? And then here is some gas right here, all right? And there's other dust, as you see here and here. But this gas is oxygen. And this gas is hydrogen. The oxygen has a greenish glow. Now, when it's very dense, the glow is very pronounced. But here it's actually not very dense, and so it's sort of a subtle green. It's not a full-on hardcore green like we would see in a true ionized oxygen nebula. So this is oxygen, and I know that because I actually looked at the study up on ResearchGate, which showed how the elemental oxygen in the Rosette Nebula was distributed, and you could clearly see that it's in the central regions here. So, and we got a question from Mike Hedrick. Mark, I have a question all of a sudden. Oh my gosh, I have an answer. 3. Okay. How fast is nebula's expansion rate? Is it really covering all this space, or is it so close to us that it just looks like it's covering all these stars? No, it's 5,000 light years away. And by contrast, the Orion complex, the Orion Nebula, is only 1,500. So it's a lot further away. If you put the Orion Nebula in here, okay, it would only be about this big. Okay, so the Orion Nebula is actually, a lot closer to us. All right, it would actually be about that big. Maybe about that big. in this view, right? So there you go. So this is actually how big these stellar nurseries can be. This is massive, and we know it has oxygen in it. No, it has hydrogen, dust, and there you go. That's the magic soup maker for life in the universe. Pretty cool.
Definitely.
Oh, yeah. And I have to say, that's the last object we're going to look at tonight. So we will be giving people a break and letting them get back to their lives. Especially get back to the garbage that you're doing, Mike, with your cat.
Right.
The garbage. I love that name,
Right.
Garbage. That's a great name for a cat.
She's adorable. I mean, she's an absolute cuddle muffin.
Yeah,
Seriously.
she's a piece of garbage. Oh, yeah.
Yeah, right.
That's kind.
A beautiful piece of
Yep.
garbage. A giant piece of garbage.
Yeah,
A very hungry piece of garbage.
Maine
Yeah.
Coon size piece of garbage.
Right.
Great deal.
And honestly, I just realized, Elizabeth or Isabella, thank you so much for helping me with the likes and thumbs up messages. I just realized that mine wasn't going through. That's what I was checking out right now as we were ending the viewing. That's a little disconcerting.
Yeah.
I'm wondering why that happened. You don't see that at all, do you? Yeah, I was every so often, every about, I'd say, give or take 10 minutes or so, I was putting, if you haven't already, please take a moment to thumbs up, share, subscribe to the STLS channel. It greatly helps with the YouTube algorithm in reaching new people. Even commenting, everything that you guys do in these streams helps us reach new people. And thank you for doing so. Thank you for being with us.
Yeah.
As well as commenting and asking questions. Seriously, everything helps.
Yeah, and it's kind of weird, and I've said this before. I'm gonna tell you right now, it's really weird to me that I'm in Connecticut, running a telescope in Arizona. The technology's come so far that we have that availability. Now, it took me a year researching this prospect to figure out how to do this reliably long distance. I did write code. I wrote programs to actually control the telescope and the building itself from here. And I learned technologies I never knew before in order to do that. So I have to say that the fact that we're staring at this as a whole, all of us from around the world watching this tonight, is a second accomplishment that is amazing, that we can do this and bring it to the world. I'm just amazed. Now I wanted to just address a couple of questions. Michael Hedrick's asking about the expansion rate of the nebula. I don't know about that, but just so you know, but it is, like I said, 5,219 light years away from us. So it is again, in the sky, if you could hold your finger up, it'd probably be just a little bigger than your pinky nail at arm's length. Okay,
What?
That's how big it is. All right. And Blues Traveler has a question about the temperature of the ionized oxygen. I'd have to look at the ionization temperature, Blues. I don't know. But the ionization temperature of the oxygen and the hydrogen are, again, the result of these hot stars. I do want to say something too. When we talk about temperature, we got to be careful. In space, technically, there's no temperature. Things in space either absorb radiation or emit radiation. Okay, atoms in a cold gas will absorb energy that strikes them, and that energy will be absorbed by the electrons, and then will go into higher states. Higher energy states. That's called ionization when they leave the atom. Okay, right. They're in an excited state when they go to just a higher, call it an orbit in the atom. Okay, so that said, ionization is the magic thing that causes this to be seeable, something you can see. because it's absorbing energy to leave the atom, but then it gives off energy in the form of light that you're seeing right there when they recombine with the atom. All right. So that's how this actually works. All right. So, I mean, I would say that the rosette has not disappointed me. Again, it's actually really quite nice.
We just had we didn't get to do the or we did not do the this week in science, because I actually had a question for you, Mark.
Oh my gosh, I'm sorry about that. You did have it. Yeah.
No worries. This, because all of this was fascinating.
Yeah.
Like I've learned a hell of a lot this evening.
I did too.
Absolutely. The question would have been, or the question is, this week in science, was it a scientist realized that, or they discovered that the speed of light can be slowed down by the, what was it, by the, let's actually get the
something garbage.
was it like the materials between that light and us, to where it's possible. The reason why I had my question was, could it be the fact that this is occurring, that some of these stars' light might be older by a light year or two, obviously, from reaching us, and maybe possibly the further the star is away from us, would that also have slowed down that light to get to us?
Well, okay. See, Blues Traveler is saying something that's true. He says by water. If I read him right, the speed of light is referenced when you read about it in the particular medium through which it travels. The speed of light in a vacuum, 186,282 miles per second. Okay, that's 7 point such times around the Earth in a second, if you could make it go around the Earth. Okay. So bottom line is that in different mediums, we already know that light travels at different speeds.
Right. Okay.
So I'm not sure what this is. I'll read the paper if you got it. You can send me the link, and I'll check it out.
Send
Yeah.
Messenger. We'll send it through
There
Messenger.
you go. That's fine.
We could bring it up next time.
Yeah.
Definitely.
A Blues Traveler's a smart person. See, he knew what you're talking about.
He's on top.
Yeah, he is. Well, guys, I want to thank you for coming out, and not just you, Tiffany and Michael, but everybody listening and watching. I just gotta say hello to Jose Garcia. He says, I just got back from my dark sky site in Eloy, Arizona. I know where Eloy is. You know why I know? Because I was looking at areas like just south of Benson, because I'm going to be out there March 12th through the 21st. And one of the places I'm going to go is to these different dark sky sites and look for another dark sky site for SkyTour Livestream West number 2, which is going to be the next big thing. Yeah. And I won't have a solar telescope in place for the eclipse coming up, but that's okay. We're going to have a solar telescope here on the East Coast, and that'll be the third thing. So it's cool. Yeah, so Jose, Eloy is fantastic. I checked the light pollution down there, and it's really almost non-existent. So it's great. Yeah.
That's very exciting.
We might go right through there actually.
It's definitely exciting for
Oh yeah.
Absolutely.
Well, you know what? Thanks to all of you that are out there watching and listening. Those of you that are participating on our Patreon, thank you so much. We always need more people. As we expand, we're looking to add more capabilities. Thanks to you and the donations with your Patreon donations, I've actually I built a all sky cam, which I'm going to be installing when I go out. And the all sky cam has as high a resolution as this camera does right here. You're looking at almost the same high resolution, and so it'll be looking at the whole sky. And we'll be you can actually zoom in and see the Pleiades, see the Orion Nebula. They're tiny because it's an all sky fisheye lens. All right, but you can still see the whole sky in incredible detail and in color. Our current all sky camera doesn't do that. And at the end of the night, it does star trails a beautiful sweep of gorgeous stars. It does a time lapse, so you can see the whole day and the whole night.
Yeah.
You know,
Absolutely beautiful.
so really, really cool. All right, guys. Well, thank you for coming out. Really happy that you joined us tonight. It was a lot of fun out there, and thank you to this guy and that lady right there.
Thank you.
That's
Thank you very much for having us. It was
Michael
a lot
and
of fun.
Tiffany.
Yeah.
Learned a lot.
Well,
of
you
stuff.
got you'll be back. You're going to be coming back more often.
Yeah,
Yep.
absolutely.
All right. Well, folks, you have a good night, and we will talk to you later. Do you want to have anything you want to say as a last parting
Keep
comment?
those eyes to the skies, and
There you go.
yeah, clear skies to you all.
Clear skies to you all. Exactly right. All right. Well, good night, everybody. See you later.
Good night.
Oh, that was nice. She said good night. And Michael just like does other things.
Good night.
That's better. Good night, John
Just
boy. There you go. You know, jeez, you know. Ay, you know, it's hard to get good help
Morning.
these days.
Good night. Some people's morning, like Izabela, morning.
That's right. It's morning. Vince Giglio, hey Vince, good to see you, and good night. All right, folks, have a good night. We'll see you
All right.
later.